Thank you everyone for coming. So just a quick sort of outline of the plan for the meeting today. So we've got four great speakers, so Huyen, Yufei, Wenyuan and Shenyu, who are going to tell us a bit today about some of their recent work in this area of sort of using machine learning methods for understanding stochastic control problems and interaction between, I guess, what for many of us is quite a classical class of or classical approach to problems coming from sort of well established in mathematical finance, so continuous time stochastic control, and how that's interacting with problems sort of relating to machine learning challenges, or to machine learning is becoming a very big tool in understanding how to solve some of these problems. So we've got some great talks today on sort of talking a bit about where these things interact and some of the interesting questions that come out from that. So I think this is a very interesting field at the moment, so hopefully we should have some really interesting talks. And then later today we'll have, or at the end of the session today, we'll have a panel discussion. So we've got some questions for the four speakers, and hopefully have a bit of discussion about interesting challenges, where the field has come from, where it might be going, and what sort of questions are out there. But, okay, so before we get going, we're hoping to record this meeting today. If that's a problem, please let either myself or my other organizer, Christoph, I think you can probably see, or Janina from the RSS know, and we can edit you out of recordings. But please just do send us an email or message via Teams. And yeah, otherwise I think we'll go through the talks, and hopefully we'll have time for some questions and so on as we go on. Okay, do you think we're ready to start? Anything else, Christoph, I should have said? Okay, good. So Huyen is our first speaker. Huyen, if you can.
Yes,
great.
hello.
Hi, I can see you. Have you, do you want to share your slides?
Yes, so first let me thank Alex and Christoph for inviting me to this nice meeting. So today I would like to talk about some joint work with several persons. So Numerical Africa, so former colleague now in Paris 1, so Maximilien Jambin, a former PhD student who now works for Morgan Stanley, Mathieu Laurière in NYU, Shanghai, and Sun Yesong, who is currently my PhD student. So the context of this work is about. Okay, so it's about a mean field type control, so which is also known as the Makin-Vazov control problem. So it deals with a model of large population of interacting agents, or can be also viewed as robots. And so these agents interact in a cooperative way. So in contrast to the strategic interaction in Nash equilibrium for mean field game. So which means that all the agents will in fact obey or act for some collective welfare according to some center of decision, which can be viewed as a social planner or some influencers. And so it is well known that when the number of agents goes to infinity, so these mean field problems lead typically to an infinite dimensional problem, due to the fact that you need to take into account the population state distribution. So this raised some challenging issue, especially from both from theoretical and numerical point of view. And so there has been over the recent years some literature for handling with a numerical method for such kind of problems. So either using a backward SD method, so relying on maximum principle, or using dynamic programming equation, so associated to some Bellman equations. And but all this work are developed in a model-based setting. So in other words, when we assume that all the models coefficients are known. So now the question is what happens if the environment is unknown. So in other words, if we don't know all the model coefficient, and if you can take your decision only based on observation sample of your state and of your reward. So this is precisely the purpose of reinforcement learning. So where you want to learn actually the optimal control by trial and error. So in other words, you repeatedly try policy, you receive, you evaluate your reward, and then you improve your policy. And so in the literature in reinforcement learning, there are essentially two main approaches. So the Q learning, so Q for quality learning, which is based on dynamic priming, or the policy gradient method, which relies on parametrization of policies. And whatever the method you choose, a key feature in reinforcement learning is the exploration, okay, because the environment is unknown, and so you have to explore your state and your action space, okay, to discover what your strategy. And so for this, okay, it is common to broaden the search space by using randomized strategies. So there is now, of course, extensive literature in the classical. By classical, I mean without mean-field interaction setting. And so probably the main reference is the book by Sutton and Bartow, in particular, the second edition. And so now, okay, what we are interested in is to consider the case with multi-agent, so a large population of interacting agents. And so now, in this context, the main issue, okay, is to handle the population state distribution, which is an input of both your policy and of your value function. And so this has attracted some recent interest in the literature. So I mentioned here okay, different works that develop either the Q learning approach or the policy gradient, but here, to the best of our knowledge, mainly for linear quadratic mean-field control. But in fact, all these cited work were mostly done in a discrete time setting. So in other words, for mean-field Markov decision process, and mostly for a finite state space. And so in this talk, we were actually inspired by recent work of Tsunyu Tsu and his co-author, who developed in a very nice way reinforcement learning for control diffusion process. And so basically what we want to do is to extend the setting to the mean-field framework, okay, by providing a theoretical treatment of policy gradient method for mean-field control in continuous time. And in particular, okay, we rely on the recent stochastic calculus tools that have been developed for Mark-Inverse equation, in particular, all this Ito's formula along flow of probability measure. And this will allow us to design a policy gradient method, and more precisely, actor-critic reinforcement learning algorithm. So we shall focus more specifically on the linear quadratic mean-field case, for which we give some numerical illustration. And at the end, I will discuss briefly how we can go beyond the linear quadratic case to deal with some examples. Okay, so let me now formulate the problem. So the starting point is to consider a parametrization of the randomized policy. So p theta. So what is it? It is a map, okay, from time. So which take as input the time. So x is for the state space in RD. Mu stands for the population, it's a probability measure, so it stands for the population state distribution. And it maps into a probability measure okay, into the action space. It's a probability measure on the action space. And so the meaning is the following. So it means that at any time t, okay, your decision is sampled according to the probability distribution p theta. Okay, so where p theta, so at each time, depending on your current time, on your current state, and on the current population state, okay, you sample some control alpha according to this probability distribution. And then, okay, in order to encourage exploration, okay, so in other words, not just to have a deterministic policy, okay, it is now well known that it is useful to add some entropy, okay. So the entropy essentially has the effect to encourage exploration of the policy. So you can see on this graph, okay, if you use a large exploration of the policy, so for example, in this blue curve, okay, you use a uniform policy, randomized policy, so this leads to high entropy. While if you use essentially a deterministic policy in the green part, okay, this yields in fact a low entropy. Okay, and so, for example, what is popular is to use the Shannon differential entropy, okay, by assuming that your randomized distribution admits some density p theta. And so, okay, so such kind of different Shannon entropy has been, for example, largely used in reinforcement learning. So I mentioned some recent work here. Okay, so now, given this randomized policy, you define the performance associated to such a policy. Okay, so you have your state process, which follows some Martin-Weishoff equation. So its dynamics, okay, depends not only on its own state, but also on its population state. So P of xt stands for the distribution state of the population. And alpha, okay, the control, okay, is sampled according to your randomized policy, and your performance, okay, is the expectation, okay, over some running reward function, some terminal reward function, which also depend on the population state distribution. And then, okay, you add some entropy. So the entropy, so here's the Shannon entropy with some parameter lambda. Okay, so the higher is lambda, the higher you explore your action space and state space. Okay, so notice that because here we want to focus on to look at a model-free setting. So this means that the coefficient of the model, so here B, sigma, F, and G, okay, are assumed not to be known. Okay, so this is of course the crucial aspect of reinforcement learning. And so the policy gradient method, okay, so consists basically in maximizing over the parameter theta of your randomized policy, this performance function, okay, by a stochastic gradient ascent algorithm. Okay, and so if you are in a reinforcement learning setting, so in other words, in a model-free setting, okay, so the key point is actually to derive an expectation representation of the gradient function, okay, that does not involve the model coefficient B and sigma, but which involves only an observation sample of the state, of your population state, of the and of the reward, whenever each time you take some decision, okay, according to this to such randomized policy. One important point, okay, compared to the usual non-mean field setting, is that in reality, of course, you do not observe the population state distributions. Okay, so in practice, what you can observe, of course, is the state of each agent, but in principle, you do not observe the whole population state. And so how can do deal with such difficulties? So either you can use a black box simulator of the state distribution, which is in fact not very realistic, or you can update your estimation in a model-free manner, which is the approach that we shall adopt here. Okay, so now the idea in order to derive a policy gradient representation of our performance function is to use tool from stochastic calculus. And so first we introduce the decoupled value function associated to our performance function. So in other words, it is a function of time, of the state x, and of the probability distribution mu, where we consider respectively the state x, the flow of the state, starting from some random variable, and the flow of the state starting from some vector value x, where you freeze the law of the state. And so this define the corresponding decoupled value function, so which is a function defined on 0t times rd times the Wasserstein chances of probability measure. And so your performance function is simply the expectation of this decoupled value function, evaluated at the initial time. And so our purpose, is to compute, this the gradient of this function. So the first result, is to provide, in fact, a PD characterization of this performance value function. And in fact, so we have this result which says that this function j theta, can be characterized as a unique solution to this linear PD. So in this PD, so it's a PD on the Wasserstein space. So it's a PD involving the derivative with respect to the probability measure. So you have this generator. So in the first line, so you have the generator associated classically to the x component, and the second line here, the second line here, where you have the expectation, is in fact is coming from the ethos formula along the population state distribution. And so to prove this result, actually, this is essentially based on the Martingale property of your performance function plus the cumulative reward, and then applying ethos formula along the state process and along the flow of probability measure of the state process. So once you have this PD characterization of this performance value function, so on the Wasserstein space, then this is the main theoretical result. You can derive actually a policy gradient theorem. So in other words, you can obtain expectation representation of your gradient function, which take this form. So what appears in this expression? So you have the gradient of the log of the density of your randomized policy. So in other words, the score function. You have the increment of your performance value function, your reward function, your entropy, and you have some additional term, which is very specific to the mean field setting, which involves this operator h theta, which is written here in this last line. So how to derive such a policy gradient representation? So essentially, you start from the PD satisfied by the performance value function, and you derive, at least formally, your PD with respect to the parameter theta. and then you obtain another PD satisfied by the gradient. Okay, and then you use some kind of Feynman-Clark representation. Okay, in this mean field setting. Okay, so but of course you have to prove it rigorously to show that all these derivatives exist. Okay, and so what is nice, interesting with this policy gradient representation is that in fact, okay, so provided that this this operator H theta, okay, involve a known function and observable quantity. So this will be discussed in the next slide. Okay, then this expression of the gradient, okay, is amenable to actor-critic algorithm. Okay, so first, okay, what you need is to approximate the critic function j theta because you don't know it. So you will approximate by some parametric function, okay, on 0t times rd times the Wasserstein space. Okay, that you will estimate by a regression from its Martingale property. So this is what we call in reinforcement learning the policy evaluation. Okay, so you evaluate, okay, for a given policy, okay, the performance, and then once you evaluate this critic function, this performance value function, okay, you plug okay into this expression, okay, and then you can use a policy gradient algorithm, okay, based on this gradient representation of this performance value function. In practice, of course, to implement this policy gradient, you need to make some time discretization, and you can have two versions of this of the actor-critic algorithm, okay, depending how you write you formulate your policy evaluation and your policy gradient. So either in a global formulation, so in other words, if you write between current time and the terminal time, or if you write in a local formulation that is between current and next time. Okay, so and this leads to either offline or online algorithm. Okay, so now let me discuss, okay, some case, okay, where this operator H theta, which appear in the expression of the gradient, okay, is known. So it is typically the case where you are in a linear quadratic setting. So I will spend some time to this important case in the next section. Or otherwise, okay, if you have some separable form of your coefficient, okay, so if it is separable respect to the state and the probability measure and separable respect to the control, and if you assume that, okay, the function of your control, so the function capital C and then function capital F are known, then in this case, this operator, okay, will only involve known quantities. So it only involves the score function, okay, the parametrization of your critic function. And so this can be in principle explicitly computed in the algorithm. Okay. Now the next step, okay, which is important, is how to estimate the population state distribution. Okay, so as I said previously, okay, we do not want to assume that the social planner has at disposal a simulator of the state distribution. So instead, okay, what we only assume and what is more realistic, okay, is to consider that the social planner observes the state of some representative players, and then she will update, okay, the distribution along repeated episodes. Okay, so concretely, so it means that for each episode, so you observe your state xi at t at any time t, and then so it's starting from some guess of your population state distribution mu0. Okay, then you update, okay, your population state according to this rule. Okay, so here delta is a direct measure. Okay, and then so this update rule for the estimation of the population state, okay, is expected when the number of episodes goes to infinity, okay, to converge to the theoretical distribution according to the law of large number or propagation of chaos. Okay, so now we can describe the pseudo actor-critic algorithm. So okay, I will not spend too much time on this slide, but so what we how it is designed. So you fix the number of episodes, you discretize on time. Okay, you fix the learning rate. So there are 3 learning rates. So a learning rate for the state distribution, a learning rate for the critic function, a learning rate for the policies. Okay, a parameter lambda for the entropy regularization. And then what is important is to to parameterize your value function, your critic function. Okay, with so I recall that the value function is a function on time, state, and probability measures. Okay, you also need to parameterize the density of your randomized policy. And then, you design your algorithm in this way. Okay, so for each episode, you go forward in time. So you update your state distribution. So you just sample some action according to the randomized policy. You observe your state, your reward, and then you compute this quantity. So in an offline way. So which means that you assume that you observe the whole trajectory of your state, and you have an estimation of all the population state, and then you update, the parameter of your critic function and of your policy according to these rules, which is essentially based on the regression, of your critic function and on the policy gradient representation. Okay, and so alternately, you can do it online. So by online, I mean here you do not observe the whole trajectory, but you simply update based on your current observation and the next state. Okay, and so this leads to this following algorithm. Okay, and so you see that a crucial point, in to design this algorithm, is to parameterize both the critic function and the randomized policy. Okay, so in other words, you need to approximate a function on the Wasserstein space. And so what can, in general, so it can be approximated as follows. So you can use a neural network, in cylindrical form. So in other words, which takes this form. So it is constructed, with 2 neural networks. So one outer neural network psi eta, and an inner neural network phi eta, and so it is expected that such a neural network, cylindrical neural network, in fact, it has been recently proved in a paper with by myself and Shingo and Xiaoli Wei, that such a neural network, are in fact dense in the set of functions defined on the Wasserstein space. And otherwise, it will provide a good approximation of your critic function. Okay, so otherwise, so if you are maybe in a more specific setting, so typically if you are in a linear quadratic setting, you can use another kind of approximation, which where you don't really need to use a neural network. Concerning the randomized policy, p theta, so it is so you can also use some cylindrical neural network, defined on the Wasserstein space, to which you add some noise, in order to have some randomization, with the idea that when lambda is equal to 0, so you are back to the case of deterministic policy, and when lambda increase, you should have a variance for your random noise, which increase, with your parameter lambda. Okay, otherwise, if you have a more specific setting, okay, you can use also okay, some more specific form for your randomized policy. Okay, and so typically, so for if you are in a linear quadratic setting, so by linear quadratic setting, I mean the case where all the coefficients of the dynamics are linear with respect to the state, the mean, and of the control, and the reward function, okay, are quadratic with respect to the state, the mean, and of the control. Okay, and so in this case, what we can show, okay, even when we have entropy regularization, okay, is the fact that the optimal value function, okay, will be in a quadratic form, so a quadratic in this form, okay, so it is separable with respect to the time and with respect to the state and the mean of the probability distribution, where you have some deterministic function k, lambda, y, and r, okay, which satisfies some Riccati equation. And we can also show that the optimal randomized policy will be of Gaussian form, okay, with a mean which is linear with respect to the state, and it's the mean of the state, okay, and with some variance which is constant in time, which is deterministic in time. Okay, where all these functions which appear here, k, lambda, y, r, phi 1, phi 2, phi 3, are okay, expressed in terms of all the coefficients. Okay, but of course, now if you are in a model-free setting, okay, so now this means that you don't know the form of this coefficient, but okay, at least you can use such kind of parametrization. Okay, so it means that you have a parametrization of your critic function and of your randomized policy, okay, in terms of deterministic function, k, lambda, y, r, and phi also, which you can use a parametric function of time, okay, phi 1, phi 2, phi 3. Okay, and in this case, notice that you can also explicitly compute your operator h theta, okay, which is typically equal to 0, in fact, if you are in a mean reverting case. Okay, so okay, now for the end of this talk, I would like to just illustrate the result of our algorithm on some well-known example of mean field control problem, okay, that we borrow from the paper by Carmona, Fook, and Sung. So it's a model of systemic risk. Okay, so you have your state process, okay, which evolve according to mean field reverting dynamics. So it represents the log reserve of the banks. Okay, and so the aim for the social planner, the central bank, okay, is to minimize over randomize control, okay, such quantity, such quadratic expression, okay, which involve a mean field theorem, so in particular through the variance. Okay, and so in this case, okay, we have when all the coefficients are known, okay, we have an explicit solution. Okay, so which will serve as a benchmark. Okay, and so now, okay, if we are in a model-free setting, meaning that all the coefficients are unknown, okay, so we can take a parametric randomized policy in this form, so Gaussian random form. Okay, and for the critic function k eta r eta, so you have two possible choices. So either, okay, you use an exact parametrization, okay, coming from the exact form in the when you know the coefficient, so that in fact the optimal solution, okay, correspond to the particular value of the parameters. Or, okay, more generally, okay, you can simply use a neural network with time input for the function phi theta, k eta, r eta. Okay, and so here are the result. So here, if we use an exact parametrization, okay, so on the On the top left, okay, you see the convergence of the parameters, okay, in terms of the number of iteration. Okay, so you see that the parameters, okay, do not converge exactly to the true value, okay, which are in dot line. But if you look, what is more important, so if you look at the critic function, okay, compared to the exact critic function, so you see that they almost match perfectly. Okay, and concerning the policy, so here you have on the bottom left, you have the convergence of the parameters of the randomized policy towards when the number of iteration goes to infinity. So again, so here it's converged, okay, to the exact value, and you see also that the parametric function, okay, phi, okay, almost match perfectly to the exact value. So here we plot the one realization. So on the left, we plot one realization of the control. Okay, when you use a trajectory which is controlled by the learned control, that we compare to the exact trajectory of the control. Okay, and on the right hand side, okay, we compute the cost. Okay, so on orange you see the exact minimal cost, and on blue, okay, you see the cost, okay, where we use the learned strategy with exact parameterization. Okay, so now alternately, so if we use now online algorithm with a neural network approximation for the critic and the actor functions, and so you see here, okay, the in orange, in blue, sorry, it is in blue it is exact value, and in orange, okay, it is the result, okay, obtained with a neural network that we train. Okay, and so you see that it fits quite well, okay, both for the critic and the actor function. Okay, and so here again we plot the a trajectory, okay, for the learn policy, okay, and for the cost, okay, compared to the true one. Okay, and so you see that okay, this look like very similar. Okay, and so finally some validation test, okay, of the learn strategy. So we simulate, we consider 10 populations. So each population consisting of 10,000 agents, and for each population, okay, we compute the social cost with the learn policy. Okay, so either using the exact parameterization or using the neural network approximation. Okay, and so we here is the result of the initial cost, the standard deviation when we use the 10 population. Okay, and so you can compare with the exact value. So of course the exact value is smaller because it's a minimal one, and you see that okay, you are not very far from the exact value. Okay, with a relative error around 2%. Okay, so now it's time to conclude. So reinforcement learning for mean field control or also mean field game is, I think, a very exciting research topic with many applications involving a large population of connected and iterative agents and robots. So here in this paper, we have developed a policy gradient approach. So more precisely, actor-critic algorithm in continuous time, supported by theoretical analysis. This can be extended, in fact, to the case of infinite horizon, and even to the case when we have common noise. Also, there's some more technical difficulties. So we have presented here some numerical tests in the linear quadratic setting. So I present here just one test, but in the forthcoming papers, there will be much more numerical tests. And at least in the linear quadratic setting, okay, the results are quite promising and show quite accurate. The conversion of this algorithm is can be shown at least on infinite horizon. Of course, now what we would like to investigate is when we go beyond the linear quadratic case. And so in this case, the main issue is the learning of function on Wasserstein space. Okay, and for this, okay, we can use the idea is to use mean-field neural network, in particular this kind of cylindrical neural network. But there are also other kind of neural network which can be designed, okay, to approximate such function. And so this is a work in progress with Xavier Brown. Okay, so I think I will stop here, and thank you for your attention.
Okay, thank you, Ian. Thank you. Perhaps time for a quick question or two from the audience, or perhaps you want to raise your hand if you have a question. Or so, Renyuan.
Hello, can you hear me?
Yeah, yep. Hello, Ian.
Great, thanks for the very nice talk. I have two questions, like more on the details. On page 14, you showed the how agent update use the population distribution in their algorithm so that you don't need a simulator. There, it's like a combination of the distribution in the previous episode and a direct measure of the agent's current state. I want to understand how important this formula is when you show the theoretical result. Do you really need this linear combination, or what's the reason of designing that?
Okay, so I mean, you mean the reason, as I said, is that we do not want to assume that we have a simulator of the state distribution.
Oh, okay. No. I think it's important. It's a very nice idea to avoid using simulator. I'm curious why that formula works in practice, or is there any theoretical reason you design?
Yes. So in practice, so we use such update of the estimation. And in the convergence result that I mentioned in my last slide, okay, we prove the convergence using this update, of course.
I see. But so this helps in the theoretical convergence.
Yes. But for the moment, we were able to prove the convergence using this update estimation of the probability distribution, but only on the infinite horizon case. We are not yet able to prove in the finite horizon case, which is more tricky. But yes, of course, when I mentioned the convergence result, it's really the convergence result for the pseudo algorithm when everything is approximated, including the population state.
And Christophe, did you have a question? So did you have another question, Renyuan, or?
No, I'm good. Thank you.
Christophe, did you have a question, or you?
Just can you say a bit why is the infinite horizon case easier? Because there's some law of large numbers kicking in.
No. The infinite horizon is simpler because in this case the function k, okay, doesn't depend on time.
Okay.
And so it's yes, so it's simpler. And then of course it is well known that to prove the conversion of your iterations, okay, it's important conditions to prove the gradient domination condition. And so, this we are able to prove it for the moment only in the infinite horizon case, which is easier to handle.
Okay. So just to understand the setting right, so the infinite horizon case, you mean you go through the whole infinite horizon problem a couple of times for the learning, or do you split this up?
Yes, of course. In practice, you have to stop at some point because you cannot go to infinity in the algorithm. So you have to truncate your terminal. I mean, in the algorithm, you have to truncate the time, but the convergence. Okay, of course, we also have to estimate the effect of the truncation on the convergence.
And how do you decide when you truncate in the infinite horizon setting?
Sorry?
How do you decide when to truncate?
Yes, so we haven't done a numerical test in the infrared horizon. So we only prove for the theoretical convergence, but numerically, okay, it has not yet been done for the. So the result, the numerical test I have shown you is for the infrared horizon case.
Okay. All right. Thanks for the nice talk.
Okay, great. Thank you very much, Huyen. I think
Okay,
there was a bit of a gap.
I will stop sharing. No, okay.
Yeah, I think actually you already did just stop.
Okay, okay.
Good. But I think there's also a break in between after the next talk where people, I think, hopefully can answer questions if you want to stay around. But okay, our next speaker is Yufei. May, are you here? Okay, great. So
okay,
our next speaker is Yufei Zhang from LSE, who's going to tell us about exploration exploitation trade-off for continuous time reinforcement learning. So, thank you.
Okay, so hello everyone. Thank you for being here for my talk. And first, I want to thank Alex and Crystal for organizing this nice online workshop. And I really appreciate this great opportunity to present my work here. So in this talk, I would like to discuss how to design sample-efficient learning algorithm for continuous time models. And the talk is based on joint works with my collaborators, Lucas and Tanat from Edinburgh and Alan Turing Institute. So many mathematical finance problems involving control a random environment in order to optimize certain objective function. So the classical approach to solve this matter is to first describing the underlying environment with a controlled stochastic differential equation, and then solving the optimization problem using stochastic control techniques. However, one of the main drawbacks of this method is that it suffers from model misspecification error, in the sense that the chosen model may not well describe the underlying environment, and hence the corresponding strategy will lead to suboptimal performance. So recently, reinforcement learning techniques has achieved a great success in solving decision-making problem in an unknown environment. So these methods often chosen certain strategy and then interact with the environment based on this particular decision rule, and then use the corresponding consequence of these interactions to update their decision rule. So however, much of the attention, especially the convergence analysis of this type of algorithms, are focused on the discrete time setting. And in the continuous time environment, even though it is very close to stochastic control problem, then there's the convergence analysis of this algorithm is largely unexplored. So part of my research is to systematically understand the performance of these artificial agents in a continuous time environment. So before my talk, I want to emphasize that so in the reinforcement learning, the most natural thing to study is actually the policy, which is a function mapping from the observed system state to actions. So in the control terminology, it is often called the feedback control. So the reason is very natural, because that in the reinforcement learning setting, the agent need to make decisions based on the observed system state. That's why we are mainly interested in the policy. So when this underlying environment is described by some unknown parameter theta, then the first natural question is that how do we interact with the system in order to identify such a parameter? So in that, how do we learn? How do we learn the system? The second question is that can we guarantee that the policy, design policy, is continuous depending on this parameter estimation? So the motivation is that as the learning proceeds, we are going to have a better and better estimation for the unknown parameter theta. And we hope that our designed strategy based on this estimated model will eventually converge to the optimal policy. So this is often captured by this so-called robustness of policy. So the final one is mainly on the most important is the regret of a learning algorithm. So I will introduce this regret more carefully later, but you can think the regret as a measure to as a quantity to measure the sample efficiency of a learning algorithm. So in the reinforcement learning, we are learning the model to by interacting with the system. So each interacting, we are often have some cost. So an efficient learning algorithm should be able to find the optimal policy with a reasonable cost. And this is often described by the regret. So all these three questions, most existing work address these three questions on the discrete time model, especially on in particular on the Markov decision process with finite many states and actions. So the theoretical performance of this algorithm often depend explicitly on the number of states and actions, and hence it is very difficult to scale this algorithm to continuous time models with like a continuous state and continuous actions. So in this talk, I would like to address these three questions in a continuous diffusion model. And to simplify the presentation, I will mainly focus on the linear quadratic reinforcement learning problem, but I will discuss its extensions to a more general case. And as you will see that designing an efficient learning algorithm is closely related to entropy regularized control problem. And in particular, I will address why entropy help for the learning and how much entropy we need to add in order to achieve the optimal performance. So more precisely, let us consider this linear quadratic reinforcement learning problem, where we are given a parameter theta star, and we try to minimize this quadratic cost j over all possible of all admissible controls, where for any given admissible control alpha, the corresponding state process satisfies this controlled SD, where the drift depends on the parameter theta star, which is A star, B star. And we require the control to be adapted to the filtration generated by the state process, where you can think about the so-called feedback control. And here, this Q and R are given a positive definite matrix. So in the case that this theta star is known, then this is so-called linear quadratic. The previous problem is just a linear quadratic control problem, and it is well studied in the control theory. For example, we know that it has an optimal open loop control alpha star, and more importantly, this alpha star can be represented as a feedback form. In a sense, it can be represented as a deterministic function of the corresponding system state X. And more importantly, in this particular linear quadratic case, this feedback map or this policy is actually linear in the state. And the coefficient of this linear function can be determined by solving a Riccati equation depending on the parameter theta star. So on the other hand, if the theta star is unknown, then the previous problem becomes a linear quadratic reinforcement learning problem. And in this setting, because we don't know the theta star, we are not able to solve the corresponding Riccati equation and determine the optimal policy K. So then what we need to do is that we need to balance the exploration and the exploitation. In a sense, we need to decide when do we interact with the random environment in order to learn the parameter theta star, and then when do we exercise the optimal strategy when we based on the estimated model. So such exploration trade-off is often studied in the so-called episodic setting, which you can think as infinite many number of trials. So for example, let the theta hat be the estimated model, estimated parameter before the AMS trial and all the AMS episode. Then given this estimated parameter, the agent will interact with the system with a certain policy, phi m. And this phi m can depend on estimated parameter, but it will in general it can be something completely independent. And then the agent will observe a trajectory of the corresponding system state, and the state is now depending on the unknown parameter theta star, and is also driven by the chosen policy for this trial. And the cost of this trial is essentially determined by the previous quadratic cost, and then evaluated based on this chosen policy. And after this trial, the agent observes the corresponding state trajectory, and then the agent has a chance to update this estimated parameter based on all the previously observed information, and proceed to the beginning, to the second step. So roughly speaking, in this learning process, the agent will interact the system with a sequence of suboptimal policies, because that the agent does not know the true parameter. So then the performance of this sequence of suboptimal policy is often measured by the regret, which is defined by this quantity R for each capital N. So, okay, so the first term here, J is the cost for the mth trial. And the second term here is the optimal cost the agent can achieve if the agent knows the true model. So intuitively, this R described the accumulated loss of the agent by exercising this sequence of suboptimal policies. So for example, if in the one extreme case, for example, the agent always exercise the same policy, phi n, in the sense the policy is the same, then this quantity, this difference will remain to be constant for all the episodes. Then essentially this R, the regret, will grow linearly in terms of the number of trial n. And on the other hand, if the through the learning, if the agent was able to design this policy phi m become closer and closer to the optimal policy, then this regret R will essentially this difference will decay as m increase, and the regret R will essentially grow sublinearly in terms of the number of trials n. So what the goal of this the agent is to design this sequence of suboptimal policies such that this R, the regret, grows as slow as possible in terms of the number of trials. So so in order to design optimal learning algorithm, the first natural idea is that we need is to interact with system in order to study how do we learn these parameters A star and B star. So in this case, it's reduced to this particular case where we are given the agent fix a certain policy and try to estimate this parameter theta star based on the observed system state X. So here I want to emphasize that the agent observe the system state X, and also along this state trajectory, the agent was able to evaluate what is the corresponding control trajectory, because that the agent the policy is chosen by the agent, in the sense that the agent knows what is this z, but the agent does not know the corresponding Brownian motion path. This is the crucial difference between reinforcement learning and stochastic control. So because that if the agent knows this corresponding realization of the random noise, then the agent can essentially just move this Brownian motion path to the left-hand side and was able to figure out this unknown parameter theta with one trial. So in order to learn this parameter theta star, then we essentially design a learning algorithm based on the Bayesian perspective. So more precisely, we are going to view this theta star as a hidden random variable. And then because that here this the drift of this state dynamic depends linearly on the parameter theta star, and then we have additive Brownian motion increment, then a Brownian motion noise. Then basically by the classical linear filtering theory, we know that if before this trial, if you assume this theta star follows from a Gaussian distribution with certain mean and variance, then after this observation, the corresponding posterior distribution of the theta star will also be a Gaussian, where the mean and variance can be expressed explicitly in terms of the prior distribution and also the observed information. So roughly speaking here, the theta hat, the mean, will essentially be our estimator for the unknown parameter theta star. And the posterior variance essentially describe the uncertainty of this parameter estimation. So what we hope is that through the learning, this posterior mean will essentially converge to the optimal parameter theta, the true parameter theta star, and the uncertainty V will essentially goes to 0, which essentially says that this posterior distribution will essentially collapse to a Dirac distribution supported on the true parameter star. And also we hope that this uncertainty V will describe the convergence rate about this parameter estimation. And actually, this is indeed the case, which is essentially shown by this algorithm. By showing this theorem, which says that basically the parameter estimation accuracy can be described in terms of by the magnitude about this posterior variance. So if you write down what if you use this linear theory, this linear filter theory, and write down the explicit expression about the posterior variance, then you can show that this posterior variance can be described by the variance of the prior distribution, and also the this information matrix observed at the mth trial. So then you can see that essentially this posterior variance will collapse, will decrease, or this minimum eigenvalue about this quantity will increase if and only if this this information matrix is positive definite, and also if and only if the observed control trajectory is linearly independent about the corresponding state trajectory. So this result is essentially summarized by this theorem, which says that for any given policy, phi e, so if this policy satisfies a corresponding linear independence condition, then the agent, and if the agent exercised such a policy infinitely many times, then the agent was able to recover the optimal parameter, the true parameter based on all the observations. But of course, in practice, this such policy may be really far away from the optimal policy you want to achieve. So if we focus on the particular a policy which is linearly in the state, which is essentially the form of optimal policy of the linear quadratic problem, then we can refine this the previous result in terms of this statement, in the sense that for any estimated parameter theta, if we solve the corresponding linear quadratic control problem based on this estimated parameter theta, and then look at the corresponding optimal policy, then such a greedy policy allows you to identify the parameter theta star if and only if your estimated parameter b is the full column rank. So recall this b is the coefficient before the control variable. So what it says is that if your optimal policy, if your optimal parameter b star is not full column rank, then in general you don't expect that you can always exercise the corresponding greedy policy based on the estimation, and then achieve a convergence result. So this observation essentially leads us to this so-called phase-based algorithm, where essentially we are going to alternate between exploration phase and the exploitation phase. So this algorithm will operate in cycle, where this cycle is indexed by k. So for the case cycle, we are essentially each cycle has two phases. We have the exploration phase and we have the exploitation phase. So for the exploration phase, we are going to exercise a certain exploration policy for one trial, and then based on this observed information, we update the parameter estimation by using the previous Bayesian inference rule, and then based on this estimated model, we are going to compute a linear quadratic control problem with the estimated model, and then exercise the corresponding greedy policy with MK trial. And this this function MK will be determined later. So after this exploitation phase, we go to the next cycle, and then we are going to do exploration once with the same exploration policy. So roughly speaking, this function m will determine the exploration and the exploitation trade-off. So for example, if this m is relatively small, then essentially we are emphasizing more on the exploration, because we always exercising, for each cycle, we always exercising do one period exploration. Well, if this mk become larger and larger, then we are eventually emphasizing more and more on exploitation. So in the later, I'm going to determine such a function m by to minimize the regret of this learning algorithm. So in order to do that, let us recall the definition about the regret. So the regret up to the nth trial is essentially determined by the accumulated loss of all the previous trials. So because of this design about this particular phase-based structure, we have an explicit separation between exploration and exploitation, in the sense that all these nth trial can be split in terms of exploration episodes and also the exploitation episodes. Where for the exploration episode, we always exercise the same exploration policy. So then in this case, you see that this the loss from the exploration part is actually grow linearly in terms of number of exploration up to the nth trial. And then the second term is essentially the loss from coming from the exploitation part, where we exercising a greedy policy based on the estimated model. So in order to control the loss from this exploitation phase, we approve the second performance gap, in the sense that for any given parameter theta, if you compute the corresponding greedy policy, then the difference of such a greedy policy to the optimal loss you want to achieve depends quadratically on this parameter estimation. So in the sense that this performance gap quantifies precisely how this model estimation error impact your decision. So using such a performance gap, you can essentially replace this the difference in this bracket by the quadratic by the square about the parameter estimation error. So then you see that the first term here, this exploitation cost, will increase linearly in terms of number of exploration episodes, where the second term you will essentially decrease as if you explore more and more frequent, because the parameter estimation will become more and more accurate. So what you need to do is that you just try to balance these two terms. So indeed, this is what you can do by for the for the case cycle. We are going to exploit k episodes, and then we are able to get a square root regret of this learning algorithm. And this square root regret is what you can expect in the general case. Actually, you can Xunyu recently has a very nice work, shows that actually this square root regret is actually so this regret is essentially lower bounded in terms of with the square root order. So in the sense that such a choice is optimal in terms of the regret order. So so recall that, but okay. So in the previous okay, so our currently we have already discussed about the learning algorithm where we have an explicit separation between the exploration phase and the exploitation phase. So, but this type of analysis can be extended to other exploration strategies. So, for example, there is commonly used exploration strategy, which is often called a naive exploration. So, in this such an exploration strategy for the mth trial, given the estimated model theta hat, the agent just will exercise a randomized policy, as what Huynh introduced in his talk. What we do is that we are computing the corresponding greedy policy, and then just perturb this greedy policy with some noise. And this noise is essentially designed by the agent for the exploration. So this independent noise essentially make this corresponding control linearly introduce some linearly independence between the control trajectory to the corresponding state trajectory, which essentially helps for the exploration. But on the other hand, the choice of noise also determines the exploration and exploitation trade-off. For example, if you have a larger independent noise, then intuitively this policy will be more satisfy this independence condition better. Then you have better exploration effect. But on the other hand, it will be this policy will be deviating from the corresponding greedy policy more, and then you have a larger exploitation cost. So in a recent very nice paper and by Wang, by Haoran, Talia, and Xunyu, they propose that such a noise can be designed systematically by solving a corresponding exploratory control problem. And we are going to proceed along this line in the remaining part of the talk. So what is the exploratory control problem? Essentially, the exploratory control problem extends the classical linear quadratic control problem from two aspects. So the first aspect is that it enlarged the class of admissible policy from deterministic policy to stochastic policy. So more precisely, for any given time and space, instead of determining a concrete action, we are going to determine distribution supported over all actions. And the second point is that we are going to add entropy of this such stochastic policy explicitly in the loss function. So you can verify that in this such a linear quadratic setting, for any given parameter theta and for any given regularization weight, the corresponding optimal exploratory policy is essentially of this Gaussian form, where the mean of this Gaussian is exactly the same policy as the same greedy policy as the classical linear quadratic problem, where the variance of such variance of the policy scales linearly in terms of this exploration weight rho. So here I want to emphasize that this exploratory control problem is just a tool to design the corresponding strategy, and our system is still the original linear quadratic the original linear dynamic. So then the natural question is that how do we interact with the system given such this randomized policy? So the natural idea is that we are going to implement such exploratory control by randomization, as I already introduced before. So more precisely, given such a Gaussian policy where we have a mean depending linearly in state and we have a variance just a time-dependent function, we are going to introduce by such a piecewise constant manner. So what I do is that I will partition the whole time interval 0t in terms of several sub-intervals, like n sub-intervals. And then at the beginning about the interval t0 to t1, I'm going to randomly sample a normal random variable, and then scale this normal random variable based on the corresponding standard deviation, and then just use this as a perturbation of the corresponding of this called the mean of the mean of this Gaussian policy. And then we are going to exercise a policy to interact with the system between t0 and t1. And at the beginning of the t1, I'm going to resample another independent random variable, a normal random variable, and I use this as a new random perturbation and interacting with the system based on such a randomized policy. So we can actually prove that in high probability, this such randomized policy will converge to the corresponding exploratory control with the explicit bound in terms of the frequency about this match size, and also in terms of the magnitude about this Gaussian policy. So such this explicit dependence on the magnitude is essential for us in order to determine to balance the exploration and exploitation trade-off. So this result also holds almost surely, and also you can derive a similar convergence rate in terms of expectation, where the precise statement is given in our paper. So basically the take-home message is that essentially this exploratory policy is actually coming from a law of large number in time. So the crucial point is that all these independent samples must be independent across time. So now with this such given this such a randomized execution, we are able to present this our learning algorithm. So what we do is essentially we start from a some parameter estimation θ1. We are going to solve the corresponding linear quadratic control problem, a linear quadratic entropy regularized control problem with certain entropy regularization parameter rho m. After determining that, we are going to exercise such a Gaussian policy by using this piecewise constant randomization on a particular time grid. And then based on this information, I'm going to update the parameter estimation and then proceed to the step 2. So basically, we are eventually, by optimizing the size about the regularization and also the size about this mesh size, we are able to recover the optimal square root regret. So here, this theorem, the proof of this theorem is much more challenging than the previous one, because that here, we are doing, so our learning algorithm is simultaneously exploring and also doing exploitation. We don't have this clear separation between the exploration phase and the exploitation phase as the algorithm one. And the crucial step is actually to quantify the decay rate about this posterior variance in terms of the magnitude about this injective noise, or in the sense that the magnitude about this regularization parameter. So the final part about this, my talk, I will essentially comment on a possible extension about all these analyses. So in this talk, I'm mainly focused on the linear quadratic problem, where we are controlling a linear dynamic, and then we are optimizing a quadratic cost function. So but our analysis can be extended to more general setting. For example, we can replace the system noise from just a Brownian motion increment to Brownian motion increment plus some jump, where we can allow this jump to be a general compensated Poisson process. We can replace this quadratic cost to some convex cost function, and which can potentially be non-differentiable. So the learning algorithm almost stays the same, but the analysis will become much more technical. The key challenge is actually to determine this performance gap, in the sense that also to or more precisely this performance gap. So in the sense that we need to know if we make certain error in terms of estimated model, how this model will impact our decision. So in the linear quadratic case, this is achieved by studying the corresponding Riccati equation, because in the linear quadratic case, we know the given model, the corresponding greedy policy is linearly in a state, and the coefficient is captured by the Riccati equation. So in a more general, for example, in a general convex cost, the corresponding optimal policy is no longer linear in state; it becomes nonlinear in the state, and we are able to characterize the corresponding policy by using a coupled FBSD. So in this case, we are going to study a sensitivity about coupled FBSD, forward-backward stochastic differential equation. And then we are able to prove that this performance gap is still quadratic if the cost function is smooth enough, or in general, we can get a linear performance gap if the cost is non-smooth. And then the detailed analysis is described in this paper. So to summarize my talk, essentially in this talk, I described analysis about the regret analysis for model-based reinforcement learning. So essentially, the regret can be decomposed in terms of two parts. The first part is the convergence rate about a parameter estimation. And the second part is essentially the performance gap of greedy policy. So the parameter estimation part can be studied by using statistical learning theory and plus some concentration inequality. And the second part is essentially studied by control theory. And we demonstrate that by optimizing the exploration and exploitation trade-off, you can get the optimal regret, at least if the dynamic depends linearly on the unknown parameter. So the talk is essentially based on these two papers, where the first paper we studied this phase-based learning algorithm for linear convex model, where the second paper we describe carefully about how to choose this entropy regularization for linear quadratic case. And this is the end of my talk. Thank you.
Thank you, Yufei. Very interesting talk. Time for a few quick questions before the break. If anyone has any? Jonathan, yet in the audience?
Hi, Yufei. Can you hear me?
Yes, I can.
Hi. So my question is, so in the linear quadratic control problem, if you know the coefficients, then the policy is deterministic, right? So here you're trying to learn what the parameters are. So you're introducing this regularization term to explore. So I was wondering, in your algorithm, do you tune this the amount of regularization you do as you explore more and more? So like at some point you converge towards like a more deterministic policy as you have more information of your after exploration?
Yes, we tune that. This is essentially, can you see my slides?
Yeah.
Okay, so this is essentially stated in this algorithm, as you see.
Okay.
So as the number of trials increase, essentially this entropy regulation decays with like a 1 over square root.
Okay, so at each time step, your regularization term decreases.
Yes,
Okay.
and it decreases in a deterministic way at this moment.
Okay. Thanks.
Just to follow, I mean, so it's decreasing deterministically because you can handle that and understand it? I mean, or, I mean, yes. If you could, I mean, is there some way to sort of, would there be some way to learn this or base this on your experience? Yeah, so this is a very nice question. So we do it a deterministic way. So first, I think it is relatively easier to implement, to make a deterministic, and then most existing work do it in a deterministic way. And actually, to be honest, because that we originally want to make it to be stochastic, because we want to make this regularization to be adaptive to the current observation. So in a sense, that maybe it should depends on your parameter uncertainty, for example. But when we do this work, there is some technical difficulty we are not able to overcome. But I think now we after finishing this work, we have better understanding about this analysis, and we can make it to be in a so-called feedback way. So that this one decrease is basically it does not have a deterministic decay, but it depends. The decay depends on your parameter uncertainty, essentially. Okay, thank you. Let's see, there's another question from Renyuan.
Hello, Yufei. Thanks for the very nice talk. I have a quick question about the first part when you showed the PEJE algorithm. So you only use the data in the exploration phase to estimate the parameter, right? I was wondering whether there will be any improvement if you use the data from the exploitation to do the estimation. I understand that this is already optimal in the sense that the regret is square root of n. I was wondering whether there would be some improvement in the constant term if you include more data in the estimation part.
Yeah, it's a very nice question. So actually, I present this formula in the talk. It's just for, I think it's relatively simpler. But actually, in the paper, actually we update the parameter theta all based on all previous information. So in the general case, you don't expect you expect empirically it will be better because you don't throw away information, right? So in the statistics, you always want to use all the available information. So actually, we can prove that this under certain case, if your true model B star is actually is already full rank, for example, then you have this self-exploration structure. Where in this case, so if you are able to prove that your exploration the information from your exploration episode also help you to to improve the parameter estimation, then you can actually if you update the parameter theta based on all the previous observation, you can obtain a logarithm regret, and which is much better than this square root purely based on the exploration episodes. But this one is only under special case of the model.
Sorry, I had another question about your talk, if that's okay.
Sure. Let me just switch out my camera. Yes.
You showed these convergence of your so you had the sort of the numerical plots where you had a convergence of your sort of estimates of the values to the and they weren't quite converging to the true ones.
Yes.
Is this, I mean, have you seen whether this is sort of stable somehow? I mean, if you ran the whole thing again with, I guess, a different random initialization or something, would it converge still to the same incorrect values? Or if you run it longer, will it converge to the truth eventually? Did you have some sense of?
Well, so it's in fact the results are somewhat different concerning the parameter of the critic and of the actor policy. So it converges better for the critic function. Sorry, for the policy parameters, while for the critic function the convergence is less stable. We don't know why, but so the convergence of the eta parameter, so for the critic function is less stable than for the actor or the policy parameters.
Am I correct? This is the one that was on the left where it seemed to converge.
Yes, the one on the top left. The top left.
Yeah.
The top left.
But
yes. So the convergence is maybe not so stable, but I think what is important is at the end the function itself, because and so if you look at the function itself, the function itself match rather well to the true function. Even if the parameters does not fit perfectly, if you look at the function, the parametric function, it fits well with the exact one.
I mean, is there somehow that the system is getting stuck in a local minima, which is very close to?
Yes. So yes,
something close to it.
Yes, for the iteration, we stop when it becomes. I mean, I don't know if it converges to a local minima, but it's. Well, so I mean, as I say, for the critic function, it does not converge to the true value. So in fact, we even have there is some gap between the convergence value and the true value, at least for the critic function. But for the when you look at the function itself, it fits well. Also, the parameters does not converge exactly. The critic function converge.
Yeah.
So I have another question, which is similar to Ren Yuan's question about. It's essentially about this this update for the law dependence.
Yes.
So for each trial, essentially these xi are generated by different policies, right? So you are taking this based on the previous empirical measure and update and a convex combination of the current Dirac measure supported on the current system state. And this system state, essentially, they are generated by different policies, right?
Yes.
And then intuitively, why these quantities can converge to has a limit, or do you have any? So in terms of convergence analysis, is it because of the special choice about this learning rate rho, or?
Yes. So in principle, if you take a learning rate, which is for example 1/i, so you know by the law of large number, because essentially this updating rule is correspond more or less to the empirical measure of the xi.
But they are empirical measure of different. Okay, so this xi they are empirical measure for different state, right?
Yes, for different state, but intuitively the state will converge to the when you update your parameters, so you improve your estimation, and so of course, yes. And each time it becomes more and more precise.
Okay, and
whenever you go along the episode, so the parameters becomes more precise, and then.
I see. So then, in order to preserve this convergence rate of the classical like policy gradient method, and then what is the? Maybe I can wait for your paper, but what is the dependence? What's the choice of rho in order to preserve?
The choice of rho is yes is so actually yes. So in theory, you can take for rho any sequence that satisfies Robinson rho condition, but in practice Okay, the row may vary along the episodes.
All right.
Thank you.
So more or less it's 1 over I or something like that.
Thank you.
Okay, great. Thank you very much. So welcome back, everybody, for our second session. As you know, we have 2 speakers now, and afterwards we are planning a panel discussion with the speakers. If you have any questions from the audience you would like to ask the speakers during this panel discussion, feel free to put them in the chat so that we can read them out later. And now it's my pleasure to introduce Renyuan Xu. I hope this is pronounced roughly correct. She did her PhD with Xingu at University of Berkeley, then did a postdoc at University of Oxford in the UK, and now is at the University of Southern California. And today she will speak about system noise and individual exploration in learning large population games. Thank you very much for giving this talk.
Thanks, Crystal, for the very nice introduction, and thanks, Alex and Crystal, for organizing this great workshop. And I learned a lot from the first 2 talks. Thanks for having me here. Let me start with sharing my screen here. Can you see my screen?
Perfect.
Okay. Hello, everyone. Today I'm going to talk about how system noise can help in learning large population games, and how should we incentivize individual exploration in this in the game setting when we have very limited information about the environment and we have a large group of competitive players. So this my talk is based on 2 papers. The first one is a joint work with Ben from Oxford and Hui Ning, who is currently a postdoc in Princeton. And the second part of the talk is based on a paper, joint paper with Xin and Thalia. So multi-agent reinforcement learning is a framework to learn to make decisions by interacting with an unknown or partially unknown environment, and by interacting with other strategic agents. So we focus on a discrete time framework here. So at each decision time t, our agent I will take an action uti at a given state xti. So this is a private. This is a state of agent I. Then the agent will observe an instantaneous reward function and then move to the next state xt plus 1i. So as Yufeng introduced in the single agent setting, very similar here. In the learning environment, agent I typically don't know the functional form of R, or if R is random, the agent doesn't know the distribution of the of this random variable. We will after the agent makes a decision, he will observe a realized reward. So it's a sample from an unknown distribution. And in the learning environment, the agent typically doesn't know the transition kernels going from xt to xpt plus 1 as well. So the agent doesn't know those kind of information. And for notation convenience, we use this bold xt to denote the joint state profile of our agents, assuming that we have n players in the system. And this ut denotes the joint action profile from all the agents. So this learning framework is very general and flexible because it embraces the big data era with fewer model assumptions. We don't need to make necessary assumptions on the distribution of the reward function, nor any assumption on the transition kernels. And it can help us to construct decision policies and estimate agents' value functions by only using samples that we could collect from the environment. By samples, I mean this xt, ut, and rti tuple running from the state starting time t equals to 0 and the terminal time capital T. And we can repeat the game episodically to collect as many as data we want, and then help the agents to improve their decisions in the environment. So this would be the general setting that we focus on today. So this multi-agent reinforcement learning is closely related but different from our classical stochastic control and game theory setting. So the difference is that in the control literature or game theory literature, we often assume that the environment is fully given. From a discrete time description, that means the transition kernel of all the agents is given, and we know the distribution of the reward random variable. Okay, but there is a very strong connection, which I think it's the focus of this workshop today. So many reinforcement learning algorithms are actually designed based on tools developed from our stochastic control and game theory. For example, many iterative algorithms are designed based on Hamilton-Jacobi-Bellman equation and dynamic programming principles, or even the viscosity solution. And the convergence of these algorithms are based on the convergence of some iterative numerical methods for solving control problems. And we also see some recent interest in applying single agent or multi-agent reinforcement learning algorithms to financial applications such as optimal execution, portfolio optimization, hedging, option pricing, market making, and etc. If you are interested in these financial applications, please take a look at our recent survey paper, which was available online last year. So what are the main difficulties of applying or showing some theoretical guarantees for reinforcement learning algorithm in the large population regime? Because the main difficulty comes from the complex nature of game interactions among individuals, and very often we will face the difficulty that different agents in the system have different information structure. And this makes it hard to show the convergence and theoretical establishments in this setting. Okay. And a few questions that we are interested in investigating or understanding is that how individual agents in this large population regime should explore information, and what kind of information individual agents should look for. And another question we are interested in is whether random exploration will increase the chaos of the system. We want to understand whether this is a good thing for learning or not. So we will try to address these questions through a very simple framework. So it's a linear quadratic framework plus the policy gradient method. We want to focus on policy gradient method is because this is very easy to implement, and it has many variations, and we can add constraints and we can adjust the algorithm based on the setting of our problem. And this algorithm is also suitable for continuous state and continuous action space. We don't need to restrict ourselves to the finite state and finite action setting. But this is a very popular algorithm in practice because it doesn't require any domain knowledge to implement this algorithm, and it can give a decent performance for many different applications. So it's a very good starting point, but it often lacks of theoretical guarantees in terms of the optimality, the convergence, sample complexity, or the regret analysis. Only in recent years, we've seen some very interesting developments along this direction. And the reason we want to focus on linear quadratic framework is because it's a very simple framework with analytical structures, and we know a lot about the well-definedness, controllability, stability properties of this kind of framework from the control literature. So we have a lot of existing tools that we could borrow to analyze the convergence for the learning algorithms. And in the learning literature, existing papers focused on zero-sum linear quadratic games when there are only two players, and the convergence of policy gradient method for general sum games has been a difficult problem, and we would like to give some initial investigation on why this is a hard problem and how should we modify the existing framework so that we could get some theoretical performance analysis. So this is the outline of my presentation today. I will start with the multi-agent problem and show under what conditions we could derive the global convergence result for the policy gradient method, and then we will do some small experiments to show the effect of system noise, and then we will move on to the mean field regime to perform some systematic study of exploration noise through the notion of entropy regularization, and we will show how to stabilize the training process of this learning problem in the mean field regime via the entropy regularization. So our motivation of studying this linear quadratic game is actually coming from this paper by Manzunda and his co-authors, which is published in Journal of Machine Learning Research in 2019. So the paper of the name is called Policy Gradient Algorithms Have No Guarantees of Convergence in Linear Quadratic Games. So it is an empirical paper. They did many interesting experiments to show that under a lot of situations, this algorithm fails to converge, and this is one of the examples they proposed in their paper. So it's a two-player, general sum game where they focused on deterministic dynamic in an infinite time horizon. So they showed that if both players perform a policy gradient descent type of algorithm, then their value functions will oscillate around the theoretical Nash equilibrium value without ever converging to it. And if we look at the trajectory on the parameter space, we see that after 5,000 iterations, the value of the parameter just oscillates around the Nash equilibrium point, but without converging to it. So we were very curious and we want to understand why that happened and what are the minimum conditions we could propose to make the convergence actually happen. So we actually showed that if we focus on the stochastic dynamics and we investigate in the infinite horizon problem, we can actually show the global convergence of this policy gradient type of algorithms. And after I introduce the mathematical setup and our main result, I will also talk about the insights on why stochastic dynamics is important for learning and why finite time horizon would also be possibly helpful. So this is the setting of our n-player general sum linear quadratic games. We have n players in the system, and as Yufei introduced for the single agent setting, we know that if we focus on linear quadratic games, then the Nash equilibrium, the Nash equilibrium policy would be in this linear feedback form. So instead of learning the control UTI, we could just learn this parameter in front of the current state, because the optimal policy is a feedback policy in its linear form. So it's linear in the current state. So we can do it like this. And xt is the joint state of all the agents. So it's a linear dynamics. Xt plus 1 is linear in xt, and it's also linear in individual states. And we have a system noise Wt here, which follows a sub-Gaussian distribution. And for each player I, the goal of player I is trying to minimize this quadratic cost function here, and we use this bold k to denote the policy parameters of all agents. So we see that if we restrict our agents to take this linear policy, then we can write this cost function ci as the cost function. Okay, so the difficulty of learning this problem is that we could show this ci is non-convex, so it's not convex and not concave in the parameter k. And our goal is to learn the Nash equilibrium policy under some conditions that this existing Nash equilibrium policy would be unique. Our goal is to design some algorithm to learn this Nash equilibrium strategy under this framework. Okay. And we know that, so there are two steps. When we have the access to model parameters, saying that we know what the value of AT, BT, QT, and RT are, then the way to construct a policy gradient step is to first take a gradient of the current cost function with respect to the control parameter. Then we update our current policy KTI to KTI prime by descending according to this decision, according to this direction, and we regularize the gradient direction by this inverse of the state covariance matrix, because this can speed up the convergence because this is related to Fisher information, and it gives us the steepest descent direction on the statistical manifold. But later on, we showed that even without this regularization, the algorithm will still work. So this is under the setting that we know all the model parameters. However, in the learning setting, we won't be able to calculate this expectation here because we don't know the model parameters. So we won't be able to calculate the C and its derivative. What we could do is to use whatever is available to us. So we have observable quantities here, and we could use these quantities to construct some unbiased estimators for the gradient term and the state covariance matrix, or the second order movement of the state process. So we can use some zeroth order approximation method to approximate these two terms, and it's very similar to the finite difference method in the numerical analysis literature to use this difference to approximating this gradient term. So on a high level idea, this is what we did to estimate these unknown quantities by using the samples that we could collect from the environment. So the key assumption I want to share with everyone today is that under the assumption that the system has enough level of noise, then we can show that this algorithm actually works. So this sigma x is the minimum of two terms. The first term is the smallest singular value of the expectation of the state covariance matrix, initial state covariance matrix, and the system noise. So we could show that if this sigma x is bigger than certain value, and this quantity depends on how many agents are in the system, how long is the time horizon, and what's the dimension of the state process. So this f is some explicit function of these model parameters. If this assumption is satisfied, then we can say something about the algorithm. And here are some comments I also want to share. So the system noise can either come from the underlying dynamics or some carefully designed explorations from the agents, because when the agent explores, when he or she add noises to her policies, that noise will be introduced to the dynamics as well, and that could help us to increase the level of noise in the system. And in practice, we could show that the algorithm may still converge when the key assumption is violated. But one nice direction to look into this problem is that system noise could help us to learn and to learn to find the Nash equilibrium strategy. So this is the global convergence guarantee we could establish. So under some very mild conditions, under model parameters and the system noise condition we just described, then the natural policy gradient method could reach the Nash equilibrium strategy with an error epsilon when we run the algorithm for m iterations, and this m is on the order of log 1 over epsilon. So in the optimization or learning literature, if the sample complexity is on the order of log 1 over epsilon, then this is called a linear convergence. So for a non-convex, non-concave problem, the best global convergence guarantee is linear. So in that sense, we have this optimal sample complexity for our algorithm. So the key idea to perform the proof here is that we want to show the gradient dominant condition. The gradient dominant condition says that the difference of the cost function evaluated at ki when we fix the other agents to play the Nash equilibrium strategy, and the difference of this cost function with respect to the cost function of the Nash equilibrium could be upper bounded by the Fubini norm of the gradient term. So when this gradient term is small, then we know that our cost function is close to the cost function of the Nash equilibrium. And when we are trying to show this gradient dominant condition, system noise actually helps us to get this guarantee so that we could use an iterative way to show this linear convergence. Okay. And a few comments on why finite horizon and system noise may help is that when we are focusing on a time-dependent problem, the optimal feedback policy is also time-dependent, and this can help the agent to try many different parameters in the parameter space, so it enjoys a self-exploration property as Yufei just introduced, and it can ensure that the optimal state and control process span the entire parameter space so that the agent will have a better understanding of what optimal policy looks like. And the goal or the role of the system noise is that system noise can smooth out certain undesired situations with the existence of competition. So if the agent stuck in some local optimal solution, then system noise could help them to get rid of this undesired situation and then converge to the Nash equilibrium policy that we want. And as I mentioned, the noise can either come from the original system, and when the original system doesn't have enough level of system noise, then we can ask the agents to do exploration and then increase the level of noise. I think this provides a very cute perspective on understanding why exploration is important in learning, and this also leads to the question on how should we systemically investigate how to incentivize and encourage exploration. So that would be the main topic for the second part of my talk. Before doing that, I want to end this part by introducing this experiment result here. So we went back to the experiment performed in Manzula's in the paper I just introduced at the very beginning. So when the system noise is very, very small, we see that the agent starts with the initial policy at here with this black dot. Then he or she starts to run the gradient descent algorithm, and after 10,000 iterations, the agent ends at this final position here, which is far away from the Nash equilibrium. And when we start to increase the system noise from 0.001 to 0.1, we see the agent slowly moves to the position which is close to Nash equilibrium. So this reflects the fact that from an experiment perspective, system noise do help the agents to converge faster. Or make it possible to converge to the Nash equilibrium solution. Okay, so moving forward, the second part of my talk will focus on. Sorry, is there a question or? Okay, I'll continue. So the second part of my talk would be focused on how to incentivize the agents to do exploration through the notion of entropy regularization. So for the single agent case, entropy regularization encourages individual exploration in the learning environment. So Xunyu and his co-authors, including my co-author Thalia in 2018, wrote this seminal paper on showing that the optimal policy for linear quadratic problem under entropy, under Shannon's entropy is Gaussian, and this is a very tractable and efficient formula to do exploration. And indeed, in practice, this has been used extensively in many numerical examples, but this is the first theoretical result to show it in continuous time framework. So this is a quick introduction, and I think Yufei also covered this part in details. If we focus on a policy which maps from the state space to the distribution over the action space, then this is a randomized policy. Then we could add an entropy term into our original objective function to encourage exploration. If we add this entropy term with temperature parameter lambda, then the optimal policy takes this Gaussian form. So the mean would be the same feedback linear policy as the problem without entropy, and we add an exploration, and this exploration comes into play in the variance term of the optimal policy. Okay, so this is the formulation in the single agent case. And what we are interested in understanding here is how should we explore in the large population regime when the number of n goes to infinity. In this case, instead of the aggregated version of the n-player game, we could consider a mean field population when individual agents makes decisions based on microscope information, which is the mean field type of information. Then we know that by a function of strong law of large number, the aggregated version could be a good approximation of the original n-player game. So we would like to understand how to do the learning and exploration in the mean field regime. So we'll still focus on the linear quadratic framework here. Okay, so in this paper with Xin and Thalia, we introduced two types of entropies to encourage exploration. The first one is related to self-exploration. So the agent wants to explore the system that is more relevant to her decisions and to her objective functions. So we use Shannon's entropy to do that. And because we have competitions in the environment, the agent is also interested in exploring what are the other agents doing. So we encourage this type of behavior by introducing a cross entropy. So this is related to the policy of our own of our representative agent, and also the population action state distribution of the entire population at that time t. Okay, by having these two entropies in the formulation, this would be our objective function for this mean field game. So we have a coefficient lambda SE in front of the Shannon's entropy, and we have this temperature parameter for the cross entropy term. So it's still a quadratic form. We have this mean field information term MT, which is the mean position of the population's distribution mu t. Okay, and we assume that the model parameters here are unknown to the representative agent. So what we could show is that under very mild conditions, one can find a time-dependent and mean-reverting Nash equilibrium policy, which is of this Gaussian form. And a few interesting comment is that we could see that this Gaussian exploration is very helpful because it helps us to reduce the space that we need to learn the optimal policies. So we only need to search within this class of Gaussian policies. And we can see that the ratio between lambda CE and lambda SE determines how strong the mean reversion phenomenon is. And I call this peer pressure because if you pay too much attention to other agents, then you have a stronger mean reversion behavior. And we can see that the summation of these two temperature parameters determines the variance of the exploration. So the summation of these two parameters is relevant to how much effort we want to spend for the total exploration budget. And I'll stop my presentation here with this small experiment. So we can see that by increasing the level of the exploration, we have a faster convergence here. So we will need only fewer iterations to converge to the Nash equilibrium when we have a bigger coefficient in front of the entropy term. So this reflects the fact that entropy can help us to stabilize the training when we use policy gradient type of algorithms. There are some related references with many nice papers focusing on different directions, and I'll pause here with some related papers that I discussed today.
Great. Thank you very much for this nice talk. Do we have questions from the audience? Then please raise your hand. All right, Yufei, is the first.
Yeah, thank you, Renyuan, for the nice talk. So, so is it possible to explain? I think you have a very nice interpretation about this the effect of noise in terms of and its relation to global convergence of policy gradient matter. So I was wondering whether it is possible to interpret this effect through the landscape property, in the sense that this this large additive noise will make the landscape more, for example, more convex or more smooth, or in any sense?
Yeah, I think that's a very good point because we showed that the key step is to establish the gradient dominant condition. Only when cost functions are close enough to convex functions, we could show a gradient dominant condition. So when we increase the system noise, the landscape becomes better and better, so we can show the policy gradient dominant condition. That's indeed the reason. So adding system noise will make the optimization landscapes better to optimize.
Okay, thank you.
All right, and you had a question as well?
Yes, thank you, Rayan, for a nice talk. So you have two entropies, so the self entropy and cross entropy, and so I'm wondering, in practice, or how do you balance between these parameters, so lambda c and lambda c, and so is there an optimal way to choose a parameter to explore optimally your environment? So in practice, how do you choose between these two parameters?
Oh, that's a great question. We haven't explored that direction. We just fix some constants and see how it works in the numerical example.
Okay, but so you take so they are about the same value, or you take one larger than the other?
So I think agents behave differently when we put different coefficients, because the summation of these two parameters determines the variance of the policy, and the ratio determines how strongly the mean reversion behavior have. So they behave very differently when we choose different parameters.
Okay, thank you.
Yeah.
Are there other questions from the audience? Then can I ask one question from understanding? So what information do the agents get from the actions of other agents?
So they could observe the actions taken by other agents. And
but the aggregate or the individual ones? I mean, because in the quadratic expectation, the kind of the guess would be that they only the aggregate ones. Okay, that's what they need because in the quadratic. Okay, and then the other question would be, I mean, you kind of showed this example that this regularization by noise somewhat helps to converge to the right Nash equilibrium.
Yeah.
So is there also a setting where you have too much noise that you don't get convergence?
Oh, that's a good question. Let me see if I have a picture for that. No, we didn't do any performance in the super large noise regime to see whether things will just blow up. That's an interesting question, but we didn't do that.
All right, thanks. All right. If there are no further questions, then let's thank Rian again. And let's come to the next speaker, a man who doesn't need an introduction. It's my pleasure to introduce Xun-Yun Zhou, who is currently a professor at Columbia University and who held before positions at Hong Kong University and University of Oxford. He's well known for his contribution to stochastic optimal control. And today we'll talk about Q-learning in continuous time. So thank you very much for coming, and the stage is all yours.
Okay, thank you, Christopher. Can you see the screen?
Perfect, yes.
Good. Okay, let me do the full screen. Hold on. So this look good?
Hello? Yes. Yes, okay, everything good, thanks.
Okay, great. Okay, so thank you very much for having me here. So today I'm going to talk about Q-learning in continuous time. So this is the kind of last piece, the latest piece, I should say, in a series of papers on continuous time reinforcement learning. I should mention that there was a misprint on the program. It was printed as big Q-learning, but actually it should be little Q-learning, as you see here. And actually, this is the whole point of this this talk. Okay, so that was a quite unforgivable typo. Anyway, so this is this is joint work with Yanwei Jia at my department. So this is my plan. Okay, so I will start with background motivation. And then I will sort of introduce some of the previous results regarding Gibbs exploration, Gibbs sampler, and the Boltzmann exploration. But you know, the previous three speakers' presentation basically made this task easier, and so therefore I should go through it quite quickly. And then the third part is Q-learning, so that is the this part, and then I will conclude. Okay. So let's start with the background. Okay, so now I suppose this audience are all in, audience speakers are all sort of in the area of mathematical finance and stochastic control. So we have taken for granted the so-called model-based approach, meaning that we separate the estimation and the optimization part, right? So we first have put forth a model, and then we use historical data to estimate the coefficients or parameters of this model, and then we do optimization, right? This is so-called separation principle. You separate these two phases. And for most of us, probably we don't even care about the first phase. We just say, oh, we are given a model, and you know, the diffusion model, jump diffusion, whatever, and then you know, B and sigma, or the parameters are all known, so I just do my optimization, right? So this is what we have been doing. But if you think about it carefully, this is not what people learn things, right? So the separation between estimation and optimization is like, let's say, for example, you try to drive a car, then the model-based approach is like, okay, you first need to understand everything about the car. Its components, its parts, its electronics, you know, Newton's law and everything before you learn you learn how to drive. But we don't do that, right? When I learn to drive, I actually don't need to know anything about Newton's law, for example. Yes. Okay. So therefore, reinforcement learning exactly does this kind of a different way. So it mimics humans, especially children's learning process, right? So as the previous speakers have mentioned, that you know the reinforcement learning agent basically learns the strategy through trial and error. Okay, so trial and error and through interaction with the outside environment, black box, right? So I think the next point is probably the most important point, conceptual point of my talk. So if sort of you go away with only one bullet point, and this is the one. That is, to me, reinforcement learning learns strategies directly, not a model. So reinforcement learning skips estimating a model, skips learning model. It learns strategies directly. Okay, so this is in sharp contrast with classical modeling based methods. All right, so now let me talk a little bit about the key elements of reinforcement learning. Okay, so to me, reinforcement learning is stochastic control or dynamic optimization, but without the knowledge about the environment, right? So the key, if we recall the key elements of model-based classical stochastic control, of course, we have Bellman's principle, we have HGB equation, and then we have verification theorem, right? So therefore, basically, you can solve this all at once, solve the problem all at once, and offline, in a sense. But the key components of model-free reinforcement learning consists of several steps. The first one is exploration, trial and error, so which basically, previous speakers already have discussed. The next one is given policy, not necessarily optimal, okay? Given the current policy, what is its value function? What is its objective function, right? So that's called policy evaluation, or PE. Okay? But the thing is, when you estimate the value function, you are able to use samples only. Sample means data, right? Samples only, not coefficients, because you don't know anything about the model, okay? So you can only use samples. Now here, samples can be exogenously given, like the historical data of a stock market, or can be strategically generated as a part of your learning process. So you can strategically generate samples for you to learn, okay? So samples are in sort of both ways, exogenous and endogenous, right? And the next phase is policy improvement. That is, given the current policy, given you have learned its value function, how you're going to improve it, okay? How you're going to improve it, right? And then there are several ways to do so. One is policy gradient. We have already heard this, many times. The other one is Q-learning, big Q-learning, which is somehow the focus of this presentation, right? Okay, so this whole thing is like iteratively, you learn your value function, and then you improve your policy, and iteratively, hopefully you can converge to the optimal value function, optimal policy. Okay, so this is the actor-critical approach. Actor basically is the policy, critic is the value function, right? Is everything clear? All right, so what are the pitfalls of the current study? Reinforcement learning study. Of course, it's a huge area, right? But there are two main limitations, in my view, in the existing study. One is, as also discussed in previous talks, most algorithms have been developed for discrete time Markov decision processes, and a little attention paid to the problems in continuous time spaces. But then, of course, we need to consider continuous time, because many problems in real life are continuous time problems by nature, like autonomous driving, playing video games, robot navigation. These are all continuous time problems, right? Okay. Now, the other pitfall of the existing study is many reinforcement learning algorithms were devised in heuristic and ad hoc manners, with underlying objectives not always clearly stated, right? So therefore, there is a need to sort of have understanding, theoretical understanding, overarching theoretical understanding, and a unified framework for the IO reinforcement learning methods, all right? So I thought reinforcement learning continuous time and spaces sort of give an opportunity for sort of bridging those gaps, okay? So in our work, we carry out all theoretical analysis for the continuous setting. So all our analysis theories are done in the continuous setting. And we only take discrete observations at the final algorithmic stage. Okay, so because the computer, of course, can only carry out discrete steps, right? But a good advantage of this is that you roll out the sensitivity in time step size, because you have done all the results, you have done all the analysis in the continuous setting in which you don't need a time step, right? And on the other hand, of course, there are lots of tools you can make use of, like stochastic calculus, differential equations, stochastic control, and so on. Okay, so in discrete time setting, of course, you don't have those tools at disposal, right? And another advantage is that continuous time study provide a new perspectives on reinforcement learning, which I will explain. Okay. All right. So the research questions we have are the following: how to explore strategically, because you need to try and error, right? You need to explore the environment. But when you say explore, you don't explore blindly. You need to explore sort of efficiently or strategically. Now, how to do so? The second one is how to do policy evaluation. The third one, how to do policy improvement in general, right? And specifically, how to do policy gradient. And then financial application. So these are all interesting research questions we asked when we sort of kind of started this line of research. And then, we so far we have made a few progresses. Okay, so I call it pentalage. So we have 5 papers. So each of those papers answer the questions in the previous page. Okay, so this is the first paper. Basically, it gives this entropy regularization framework, and it answers the question of how to do exploration strategically, right? Then the second question is about policy evaluation. Okay, second question, right? We turn this policy evaluation into a Martingale condition problem. Martingale condition problem. That is, in order to evaluate the policy, you only need to sort of enforce certain Martingale condition. Okay. Now, Martingale condition in turn gives naturally some objective for algorithms, right? So therefore, we sort of connect policy evaluation to stochastic calculus, Martingale approach. Then this paper, third paper, is about policy gradient. Now, sort of interestingly, we turn this policy gradient problem into a policy evaluation problem for randomized strategies. So it turns out that policy gradient is a simpler policy evaluation problem. And Huing's talk already sort of talked about that idea in the mean field control case, right? So our problem, of course, originally is for the diffusion control case. Okay. And then this paper, theorem, that's about sort of general policy improvement, right? And this one, the last paper, is to apply all these algorithms theory to a specific continuous time invariance portfolio selection. And it is completely data-driven, okay? Completely data-driven. There's no estimation of the model whatsoever. It is a work in progress. All right, so let's now look at the formulation. So I think I can go through it rather quickly because the previous talks already talk about that. So basically, we have a stochastic control problem, right? So it's just SDE, X is state, A is a control, and then you have objective function, right? So this is the optimal value function. So we call it W. So there's a running payoff, there's a terminal payoff here. And then let's first record the classical model-based approach. Now, of course, it's dynamic programming, right? So it boils down to a PD called the Hamilton-Jacobi-Bellman equation. So it says that the optimal value function W satisfies this PD. And here, this H is the Hamiltonian, which is defined in this way, right? And then the verification theorem gives you the optimal feedback control policy. So feedback control policy is just to maximize pointwisely this Hamiltonian, right? And then that gives you a map from T and X to action, right? So this is a deterministic policy, right? Because it's a deterministic map from T and X to action space. And this policy can be devised at time 0 offline. And then afterwards, you just carry out this policy, right? But then, of course, this approach requires the knowledge of the environment, meaning that it requires the functional forms of these B sigma RH, because the Hamiltonian depends on these, right? Okay. But in the reinforcement learning setting, you don't have those knowledge. Okay, so therefore, as I explained, you first do exploration, right? The exploration is modeled by distribution or randomization policies, so therefore you have to use the stochastic policies, as also previously talked about. And then once you have a stochastic policy, we call it a sampler, right? A sampler, then you basically sample the actual action to control the system, right? So when you actually control the system, of course, you still use the classical policy, but that classical policy is generated or sampled from your stochastic policy. So the problem is like you try to design a dice, right? But of course, this dice has infinitely many faces. You need to design a nice dice so that every time you just roll the dice and you control the system. All right. Okay, and then I think this pi, we have also seen this notation before. So pi is a density function, basically for each t in x. So the map is to a density function. So it's a function of a function of u, right? So this is a stochastic policy because it's a density function for a random for a random variable, right? And at each time s, an action as is sample from distribution. This, okay, and then you have this exploratory formulation. So you put a entropy regularization, right? So entropy regularization is like this. You put there this gamma is the temperature parameter that control the level of exploration, and then of course this is a regularized objective. This gamma basically is the trade-off parameter between the exploitation and exploration. Okay, and I just want to mention that this regularizer does not have to be entropy. It can be other things. Well, recently we have a paper which explore other possible regularizers. Right. Okay, so this is a general sort of regularized or exploratory formulation. Right. Now, for entropy regularization, then in this paper, which has been mentioned many times before, we got optimal distribution. So basically, it is this of this form. So you can solve the problem explicitly, right? In this form, and here this V is solve the so-called exploratory HGB equation. That is the PDE of this form. I mean, it is very good-looking PDE, but it is very different from the classical model-based HGB equation. It is different. So we had a paper actually that solved this sort of discuss the issue of existence, uniqueness, and also the convergence when the temperature parameter gamma goes to 0. Okay, so we have a paper on that. But anyway, so we got optimal distribution, which is the Gibbs measure. Actually, this is the Gibbs measure. Or Boltzmann exploration. And then, in the LQ case, it boils down to Gaussian. As the LQ case, H is quadratic in A, so that basically gives you the Gaussian. And then mean variance portfolio selection is an LQ control problem. So you can apply these, to the mean variance problem. Okay. All right. So now, we sort of come to this Q-learning thing, right? Now, I should mention that this is still only a theoretical result. This cannot be used for actual implementation because this Hamiltonian, H depends on the parameters, depends on the model parameters, which we don't know, right? So you can't use it for implementation. However, it is very important. It gives guidance for algorithm design because it gives you structure. It says that when you try to design your optimal stochastic policy, you don't need to look beyond Gibbs measure. So that already gives you sort of greatly limit the search of your policies, right? So it is still useful. It gives guidance, although it cannot be used directly yet, right? Okay. So the next is policy improvement theorem. It says that given policy pi, stochastic policy, not necessarily optimal, you construct a new policy of this one. Now, this is, of course, it resembles previous, right? The previous result. But here, except here, J is the value function of pi, which we suppose have already learned, okay, in the policy evaluation phase, right? So J is the value function of pi. So you construct this pi prime, then you can show that this pi prime is better than pi. You can prove that, okay? Moreover, if this, what we call exploratory Bellman operator, that basically is this, the operator based on this distribution, if this operator has a fixed point pi star, then this pi star is optimal policy. Okay, so therefore this gives you a roadmap of how to improve your policy, right? Okay, improvement, and then basically you just iteratively use this iteratively use this map in order to converge to a policy, to the optimal policy. But however, once again, it is still not useful directly because once again this H depends on E and sigma and so on. Okay, so you cannot use it yet. All right. So this is where the Q-learning comes in, right? Like I said, the previous theory is not implementable for learning because H is unknown, right? But then let's recall the classical stochastic control, right? This is the value function, optimal value. That's the definition. And then we have the Bellman's principle of optimality, right? Okay, so WTX is this plus, so this is principle of optimality. Of course, we all know that. And then based on that, reinforcement learning literature defines the so-called big Q function. Okay, they also call it the state action value function. State action value. So it's a function of T, a function of state X, and function of state A. So this basically comes from here, from this, except that now this A is replaced by a constant action A. Okay, so this basically says that in the first, small period T to T plus delta T, you take action A, a single point action A. Then afterwards, you just take an optimal policy, right? So this is Q delta T TXA. So this is state action value function. Now, if you know that, then you take the supremum A, and that will give you the best action, the current move. So what is the current move, okay? Now, so this is the idea of Q-learning in discrete time MDP, okay? So give an example. In chess, it is like, what should be the current best move, assuming I will always follow the best move afterwards. Now, if I can learn that Q function, right? If I can learn that Q function, then basically I know the best move at each step. Then I'm done. I just follow that. Okay. So this is the idea of Q learning, which also has been applied to this AlphaGo, AlphaGo algorithm, right? But then this is for the discrete time. How we are going to extend this, Q function to continuous time? We have a problem. What is the problem? There's no Q function in continuous time. Why? Because the Q function collapses in continuous time when delta t goes to 0, right? You see, when delta t goes to 0, the role that A plays disappears, right? So A becomes insignificant when delta t goes to 0. So in other words, you wouldn't have this QTXA, you wouldn't have a state action value function. Now, if we don't have state value function, then you cannot do supremum here. You cannot compare the action at this time moment. Okay, so therefore there's no Q function. And this, of course, people notice that in the reinforcement learning literature. Q function collapse, big Q function collapse. Okay. So now the question for us is, what should be a proper continuous time counterpart of this big Q function? Now, to do that, we do a little calculation, okay? So we continue with this Q delta T TXA pi. So we first fix delta T, okay? So this is the definition here, right? This is the definition, right? Then apply the formula, we can show that this Q delta T TXA pi is this. So actually, there are two terms. This is a leading term. This leading term is just nothing else but the value function of pi. Pi here is a given policy. So therefore, this does not depend on A. Okay. However, there's a first order term, there's delta t. The first order term indeed depend on A. Okay. So we consider the first order term instead. All right. So the idea here is the small q. So this is where this small q function, not big q function, it's small q function. The small q function associated with a given stochastic policy pi is defined as this. It's exactly the first order term. So I call this as my small q function. So why I use small q? That is because just like probability cumulative function is capital F, and small f is the density function, which is a derivative, right? Derivative. So it's the same reason here. Small q is basically the derivative of big Q. Okay. Now, so some discussions here. The small q function is the first order derivative, right? We already discussed that, right? It is a continuous time notion because it does not depend on any time discretization. This is very important. You see, this definition has nothing to do with delta t. It does not depend on the delta t. So it is a vital advantage for learning algorithm design because we know, as pointed out by this paper, the performance of reinforcement learning algorithm is very sensitive with respect to time discretization. Okay. All right. Now, once we have defined this small q function, little q function, then the previous policy improvement theory can be expressed in terms of this small q function. That is, you can improve this pi prime by only q. You can replace this h Hamiltonian by q. The reason is because this term does not depend on A. Okay, so this gives you the same distribution, right? So in other words, you only need to learn q function, the small q function under any policy pi. All right. So Christopher, how much time do I have?
I think another 5 to 7 minutes. 5 to 7 minutes. 5 to 7 minutes. Right?
Very good. Very good. Thanks. Okay. Great. Okay. So in other words, now we just need to learn this small q little q function. Okay. Now how to learn that? Well, it turns out to be a policy evaluation problem. That is, we have found a Martingale characterization of q and j together. So we can actually learn q together with j. J is the value function. Together. Okay, so this is based on this theory. So basically it says that j and the q are correct little q function, value function and the little q function if and only if this is a Martingale. This is a Martingale. Okay, and the plus some sort of constraint. This constraint must be satisfied before it can be a candidate. So j hat basically is the terminal condition, and this q hat has to satisfy this. Okay, all right. And moreover, if this pi is this q hat, can be expressed in this way, then pi is the optimal policy, and j hat is the optimal value function. So therefore, this also gives you a direction as to what is the optimal policy and what is optimal. Okay, so therefore, basically, this theorem is a Martingale characterization of value function and little q function together. It is in a similar form as the policy evaluation characterization. Okay, so in a sense, mathematically, to learn little q function is a policy evaluation problem. Okay. And because of that, we can have algorithm. Okay, now before that, of course, I need to mention that to learn a function, you have to do function approximation, right? Because function is, a function is an infinite dimensional element, right? So computer cannot handle that. So you can only do finite dimensional approximation. So this is what the function approximation does, right? So we we approximate a function f by a parametric family of function f theta, where the theta is a finite dimensional entity, right? Vector, right? So parametric form, of course, can actually, this is very important, can be inspired by problem structure or neural network. Okay. Now, actually, for me, I always advocate that you should first try to find the problem structure, because that will greatly sort of enhance your learning efficiency. Okay. If you can exploit problem structure, you have a special structure for this function approximation, that would be great. So you do neural network only as a last result. So neural network is like a nuclear weapon. It can vanish anything, but it is just overkill. In many cases, it's overkill. So I always thought that you should try to make use of problem structure. But always try that, okay? On the other hand, the marginality of M leads to two loss functions very naturally for learning algorithm, all right? One is the martingale loss function, okay? So that is MT. If MT is theta, so this is also parameterized, right? MT theta is martingale, then this goes to this should be minimized, okay? So that naturally leads to a loss function for theta. I mean, loss function for determining theta. Then you have the, the gradient descent method to find the theta, right? Another one is the martingale orthogonality condition. That is, if MT theta is martingale, then the expectation of this should be zero for any CASI. CASI is adapted processes. So we call the test function. Really should be called test process, right? So this gives you sort of a stochastic approximation type of algorithm, right? So therefore, this marginality is important because it gives you explicitly some sort of objective function for your algorithms, all right? So for details, you can look at our paper on policy evaluation. Okay, so we have very detailed discussion on how to carry out these ideas. And also the previous theorem, actually this theorem can also help with this function approximation. For example, remember these two constraints, and these two constraints actually can further narrow down the range of theta and psi, these parameters, function approximation parameters, all right? So these will lead to more special parametric form of little q function approximated q psi, potentially facilitating more efficient learning. So here we have an example, which is the linear quadratic one. So in this case, you see the parametric, because in the linear quadratic case, the little q function is quadratic in action A. So that you already have structure. So you should make use of the structure here, right? And the policy is normal, is Gaussian, right? So again, the Gaussian gives you structure. So you should make use of that, right? And because of Gaussian, you can compute its entropy. So everything is explicit. Then the previous constraints basically gives you some relationship between psi and the theta that will in turn lead to a more specific parametric form for Q. So Q is more specific as this. So you see, this kind of function approximation cannot be given by a neural network, right? Okay. So here, but we have made use of the structure. And then this is the algorithm, okay? So I guess I can just, because I think I already explained that. So first of all is you minimize the martingale loss function, so you can learn J and the Q together. Learn J and Q together. This is the stochastic gradient descent method to update theta and the psi. So now all these are observable. It's based on data samples, so you don't need to know any functional forms of the problem. And the other one is Martingale orthogonality conditions. So that gives you stochastic approximation algorithm to update theta and the psi sort of jointly. Okay, so these are the algorithms. All right, now here, this is the conclusion. So in the very beginning, right, we say that the classical model-based approach separates estimation and optimization. But the model-free reinforcement learning approach skips estimating a model altogether and it learns optimizing policies directly through either policy gradient or Q-learning. Okay, now I want to step back a little bit. So actually, reinforcement learning still learns something about the environment. What is that something? That's little Q function. Now remember, this little Q function basically is related to the Hamiltonian, right? Okay. Recall the Hamiltonian is a combination of the B sigma F and also the value function. But the value function is about your decision, right? So in other words, the little Q function or Hamiltonian is really an aggregation of the environment, and your policy. But what you need to know, what you need to learn is not those individual components like a B sigma FH, like in the classical model-based approach does. We don't need to learn those individual components. All I need to learn is an overall function, which is little Q function, overall as a whole. Now, you can see that you can understand this little Q function is almost like summary statistics. Okay, so little Q function include all the information you need in order to learn the environment and to improve your policy. So it's an aggregation. It's an interaction between the environment and your action. So this Q function involves everything, right? So from a pure computational standpoint, estimating a single function is much more efficient, of course, and robust than estimating multiple functions, let's say B sigma H, in terms of avoiding or reducing over parametrization, sensitivity to errors, and accumulation errors, right? Even from the computational point of view, that's also important. But I think it's more important conceptually. It is important that what you need to learn is really this little Q function, okay? Now, technically, you can show that the Ito's formula actually shows this little Q function can be learned through the temporal differences of value function. Okay, so the task of learning and optimizing can be accomplished in a data-driven way because temporal difference can be observed. Okay, if you want to learn those individual components, you don't have that. So you have to use more like other statistical methods, which are very limited, actually. So in other words, this Q function really gives you everything about learning. Okay, so that I think is some sort of the main takeaway from this work, right? Okay, so I think I will finish here.
All right, great. Thank you very much for this very nice talk. So let's give Tunjun applause. Are there any questions from the audience? Yes, Alex has a question.
Am I right that the problem you end up trying to learn is almost like a filtering problem? You're sort of trying.
No, it's not a filtering problem. Filtering is still trying to estimate the model. So as I emphasized many times, reinforcement learning skips I don't care about the model. It's just like I said, when you drive a car, you don't need to know the car. You just learn. You just steer the wheel. You sort of take a break and see what happens, right? Try and error. If you recall you learn driving car, you try and error, right? So you interact with the environment. You don't estimate. Filtering is still classical approach. You try to estimate the model, but model can be wrong. You may have a completely wrong model. The data may not be from the model you specified. Okay, so data can be wrong, and even the data is correct, there's also like an overfitting issue, overfitting many problems, right? Mean blur problem. So therefore here, the idea is that, okay, I skip estimating the model altogether. I just focus on learning my strategy. But this learning my strategy is not like I only care about my strategy. I learn or update my strategy through the interaction with the environment. So environment is still there, but the only thing is I don't learn the environment directly or learn all its components. I learn the overall function, which is the small Q function, little Q function.
But Maggie, maybe I'm but the Q function is appearing as a drift term in some process that you need to try and extract. So you have a noisy signal, right? And you're trying to extract a drift term.
Yeah.
So in that sense, you're trying to...
But I render my Q function through this Martingale condition.
Yeah, okay.
This is Martingale characterization, right? So it's as if estimating a value function problem. You see? Yeah. So.
Okay, yeah, thank you.
Then Yuan had a question.
Hi, Sunyu. Thanks for the nice talk.
Thank you.
If I'm correct, so from this small Q function, you retrieve the policy, right? Because there's a correspondence between the policy.
Yeah, if you know that this little Q function, then you know how to improve it, right? You see, we have a theory, policy improvement theorem. Then you can construct the next policy. Given the current policy, you have the next policy pipeline after you have learned it, right?
Okay. So at the end, your algorithm looks like it looks like very similar to Actor-critic algorithm, no? Because it's like you update between your J function and your Q function. So it's like
so it becomes policy evaluation. Exactly. The algorithm is like a policy evaluation algorithm.
Okay. So it should be comparable to the Actor-critic, no?
Oh, so it's Actor-critic, yes. So in our paper, basically, we use our algorithm, we reproduce like a SASA, SASA in the discrete time case, the SASA algorithm, we can reproduce that algorithm. And then we can also reproduce policy gradient algorithm in our previous paper. So this, in a sense, is more general. Policy improvement using this little Q function is more general. It can reproduce many other, algorithm from, many other approaches.
Okay, thank you.
Then there was another question by Jonathan.
Hi, thanks very much for the talk. So for the regularization here, you're using entropy term, right?
Yeah.
I was wondering if you looked at using, for example, like a divergence term or something, so then you have effectively a reference policy as you make these updates.
You mean using other regularizer, right?
Yeah. So like a Riemann divergence, for example, like KL or something.
We haven't used the specific KL divergence, but in a recent paper, which I already put on my archive, So we have a paper which study a class of what we call Choquet regularizer. And that Choquet regularizer can produce different exploration samplers, like Ipson greedy, like Poisson, like uniform. So therefore, other exploration measure can be explained by a different kind of regularizer.
Okay.
Yeah. So it is definitely interesting question. How do you kind of optimize, right? Optimize the problem using different or using a particular regularizer, because you have a lot of choices of regularization. Which one gives you the best? In what sense, of course, right?
Yeah.
So that would be a very interesting question.
So just wondering, have you observed empirically what could work better, or I guess in some sense these entropy terms can be nicer theoretically, but have you seen empirically?
We haven't done any, for that paper I just mentioned, that we haven't done any sort of empirical study or simulation study yet. But certainly, it can. Certainly you can, because it also has algorithm. Because, for those regularization, you can also we also have the explicit solution. You can have you can solve HGB equation kind of explicitly. So therefore you can have the optimal policy, and then based on that you can devise algorithms, I think.
All right, thank you.
Yeah.
All right, do we have further questions? No, then let's ask me a quick one. You mentioned there's an extension or an application to mean variance portfolio selection.
Yeah.
So can you already say something about the main messages there? of the
main
learning?
message is, yeah, sure. Main message is basically, indeed, the learning is doing very well in a sense. We did a very extensive backtesting, comparing with all kind of, whatever strategies in the market, which we are know of, right? Like 10 strategies. And we compare with those strategies, and it does very well. Our strategy is the best in terms of Sharpe ratio and the maximum drawdown in bear market, in bull market, in overall market, 20 years annualized return, basically outperforms. So now we are working with a fund, which we have a live portfolio. Okay, because we don't want, backtesting, of course, people can say, oh, you have a survivor bias. You only show the good results. So we have like a live portfolio starting from 2 months ago. In 2 months, our portfolio beat S&P 500 by 5% in 2 months. Remember, this 2 months is a bear market. S&P 500 went down by 13%. And our strategies went down by 8%. But the point here is we observe that our strategy is much more robust and robust during the bear market, especially during the bear market. So we are still running this live portfolio and see what happens.
All right, great. Thanks. So if there are no further questions, let's move to the next point. This was this panel discussion, and here I would like to thank all the speakers that they also agreed to be kind of panel members. If you can stop sharing your slides,
sure.
Then no problem. Then I can start sharing mine. Just a second. So here we go. Can everybody see my slides? Yes? Great. Okay, so for the sake of time, let us get to the most important questions probably first. And here this was the question about, since we're all kind of researchers in the area of applied probability, including financial mathematics, optimal control, stochastic analysis, my question would be, what do you think could be the contribution from our area to machine learning and reinforcement learning, to the research done there? So I guess we go in a reverse order of academic seniority. So let's start with Renyuan. Is this right? Or is it? No, it's Yufei, right? Yufei. It's this way.
I think so.
Okay.
Yeah, thank you. I think, I started working on machine learning very recently, especially reinforcement very recently. So only maybe slightly more than 1 year. So maybe my view is very limited. So what I feel is that so basically all this reinforcement learning, they requires exploration, right? So there is always an exploration and exploitation trade-off. And then there is, of course, different type of strategy where how do you explore and then how do you learn the system. And I think, in my opinion, it will be important to know how to, so what is the optimal learning algorithm, and in certain sense. So of course, this involves giving it a criteria and then to optimize a learning algorithm inside that criteria. And I think this is not this problem is not clearly formulated, but I think because this somehow involves optimization, and then and also involves stochastic process and then probability. So I think in this direction we may able to make some contribution, and then in order to derive more sample efficient learning algorithm.
Okay, great. So mathematics should provide a general problem formulation together with kind of characterization of optimality of optimal algorithms in this framework. Okay, great. Thank you very much, Yufei. Then we continue with Renyuan.
Thanks. So I think stochastic control is very useful in terms of developing theoretical results for reinforcement learning. From my point of view, I think essentially almost all algorithms are based on reinforcement learning algorithms are based on approximating the solution to Bellman equation in the discrete time, HJB equation in the continuous time, using the samples we could observe. So having a good understanding about HJB equation, Bellman equation from a control perspective have a lot of potential in improving existing algorithms or showing theoretical convergence. And I think another potential application of RL is to understand the training process of many supervised learning problems. For example, if we have a neural network, we want to train the neural network, the training process can be formulated as a stochastic control problem. And by understanding from the control literature on what the optimal policy behaves for this control problem can lead to a lot of insights on the designing of neural network problems. And I think for stochastic analysis, which is listed on the screen here, I think stochastic analysis is particularly helpful to understand the propagation of a neural network, because if we scale out the neural networks properly, it will converge to some ODE system or SDE system, and having some good understanding of how these equations evolve over time can also lead to a lot of useful information on the designing of the architectures and neural networks. So these are some insights from my end.
All right, great. Thank you very much. And now I'm in a tricky spot. I don't know who's kind of first, Yuan or Xunyu. Do you know?
Oh,
then okay. Okay.
Okay. Okay.
Okay, then it's you.
It's okay. So I can start if you want.
The second question, yes, please.
Okay. Yes, so I do agree with what has been said by Yufei and Zhenyan. So yes, indeed, traditionally reinforcement learning was first studied in the computer science and machine learning community, and it has attracted interest among the applied mathematicians only over the last year, and this is somewhat surprising, but finally quite natural, because indeed the framework of reinforcement learning is really stochastic control and dynamic programming. And of course, as experts in stochastic control and stochastic analysis, we can obviously contribute to the theoretical foundation of all the algorithm in reinforcement learning by maybe giving some insightful understanding of the algorithm, and to develop new algorithm for. I'm thinking, for example, to the case with mean-field control, mean-field game, and possibly with heterogeneous agents. And also, what is important, I think, is to provide a rigorous proof of convergence of this algorithm, because maybe one usual criticism of machine learning and reinforcement learning algorithm is the lack of explainability, and it's quite important to validate the numerical result in order to understand the output from our algorithm, and whether we can really trust if we in the practical implementation of our hedging or investment strategy. So at some point there is some lack of confidence and theoretical guarantee, and so it's important to give a rigorous result about our result.
Great. Thank you very much, Yuan. Chunyun?
Yeah, sure. I think I agree with all the previous three speakers' comments, and also I agree with Quim that reinforcement learning, although it has been a very active area and has shown great achievement, right? But there is a problem of this interpretability / explainability problem, black box approach, kind of ad hoc approach, And in fact, to this day, the financial industry is still sort of reluctant to take those so-called AI or machine learning approaches, because they have to explain to their clients, they have to explain the regulators, so they cannot say, "Oh, I know this is good. You just use it. Don't ask why." So this explainability problem is something that we can accomplish, especially by we I mean people working in stochastic calculus, stochastic control, differential equation, mathematical finance, because we have all these skills. We have the skill set, okay, especially in continuous time, right? We have the skill set to kind of work together to lay a theoretical foundation, so that people can confidently sort of use whatever algorithm you devise, right? So and also we can sometimes can provide how to say perspective. Now let me give an example. Just this Martingale, right? So we found out this Martingale condition for policy evaluation. Of course, later it turns out that this Martingale condition is also used for policy gradient and even this little q learning. This Martingale condition is not mathematically very sophisticated. I mean, once you realize that, it's easy to prove. It's very easy to prove. And also, there is a discrete time version of it. In other words, for all the MDP, you can also have Martingale, this discrete time Martingale thing. But kind of interestingly, we sort of look at the literature, discrete time literature. Nobody mentioned about that. This discrete time Martingale. Okay, now why this is kind of interesting, because once you realize this Martingale property, then it gives you a kind of lens, right? It gives you a lens to look at things, so that sort of algorithms, sort of ad hoc algorithms scatter around and find a common ground. This Martingale lens. I mean, it turns out that this Martingale also can be used for policy gradient, can be used for other things. Okay, so this is just one little example that we can, because we have been dealing with Martingale all the time, right? Okay, so this is something that we can contribute. Yeah.
Okay, great. Thank you very much. So now let's turn things a bit around. So if you think about the other direction, what new questions are important for research and applied probability as a result of new developments in machine learning and reinforcement learning? So what are the questions kind of coming from there? Kind of can being able to trigger new kind of areas of research and applied probability. And now, if it's okay, we start with Xun.
Yeah, sure. So I think this research, I call it a continuous time reinforcement learning. I think it's at its infancy. There's so many open questions, right? So I can only name a few which is related to my own question. They are certainly not exhaustive. They are maybe biased because I'm doing that kind of research, right? So one important thing is everybody has mentioned is this convergence analysis, regret analysis, right? So you have all these nice algorithms, how good it is. Okay, that actually can call for very sophisticated research in terms of how would you for example, I mean, we are actually currently studying this problem. This Q function actually is related to this A function, and there is a relationship. Now, how would you estimate the quality of the learning this little Q function based on the data in terms of this temporal difference data? Okay, so you basically need to estimate in a sense, it is an SDE problem. You observe the data, you estimate the coefficients. Okay, so that is a very deep problem actually. Now, that's the one question, right? The other one is, of course, like this exploration, exploitation trade-off. This is gamma. or lambda, whatever you call it, how would you determine this lambda optimally? In what sense? That is another very interesting question. Then, of course, this regularization, the choice of a regularizer problem we just discussed, that is also a very interesting question. So there are so many open questions that beg for, kind of research study.
Great. Thank you very much. Then, Ewan, what's your take on this question?
Yes. Yes. So, well, so I would say that, of course, the machine learning, deep learning, has led, without any doubt, to many new possibilities in math finance. So, just to name a few, deep hedging. So that is the finding of approximate optimal strategy by allowing to take into account the realistic market conditions beyond classical model, thanks to deep learning, that now we are able to speed up calculation for solving a high-dimensional nonlinear problem compared to traditional Monte Carlo numerical method. And I think that important advances that machine learning can trigger in finance is a development of emerging or more complex models that at some point will combine the flexibility of data-driven models that reflects the reality of the market, but often lacks of explicability or interpretation, and the classical theoretical model, which for which we can use all the tools of stochastic calculus for pricing, hedging, portfolio allocation, but which often suffer from inflexibility when we vary market data. So I think that we can probably, with machine learning, we can try to combine the best of the two worlds, in order to obtain a very new emerging model in quantitative modeling.
Great, thank you very much. Then we continue with anyone.
I fully agree with what Xu and Huiyan mentioned, and I think for many machine learning problems, it motivates us to consider some framework that are similar to what have been existed there for a long time, but they have some differences. For example, in Xunyu's seminal paper with Talia and Haoran, they showed that when you add entropy, because in machine learning they like to do exploration, randomize that actions. So relaxed control is one of the notion to handle this problem. So we gave relaxed control a new perspective or new meaning from the learning perspective. And another example is when we are looking at the training of neural network that can be formulated as a forward backward stochastic differential equation, but not in the classical sense. So those kind of questions could be connected to the existing literature, but they have new ingredients, so that there are a lot of opportunities for us to study these new problems. And another trigger in mathematical finance, I would say, is that many machine learning algorithms and reinforcement learning algorithms require a lot of sample for the algorithm to converge. But if we view financial markets as some non-stationary environment, we won't be able to have sufficient recent data to make the algorithm work. From my perspective, how to construct a realistic market simulator is also a challenging question. And if we have a realistic market simulator, maybe we can push a lot of machine learning and reinforcement learning algorithms to work in practice.
Great, thank you very much. Yufei?
Yeah, I fully agree with all the three speakers, in particularly this explainability about the sample efficiency, and also this market simulator. I think that this is actually quite important, especially this market simulation. This basically this environment simulator, because that for many particular financial application, we are given a data which is generated by some other policy. And then we want to use that to train a reinforcement learning algorithm, which requires to know what is the consequence of a particular action. So this can be, so we can either build on practical or realistic market simulator based on this previous given data set, or we can design some learning, design some algorithm to evaluate the policy performance based on data generated by other policies. I think this can be an interesting direction to go. The second is this robustness of a decision-making problem, because that now all these things we are making decision based on some given data set. So I think then we are actually practically interested in how to apply some pre-trained model to some other environment. For example, maybe a realistic market, or in a market which is maybe another stock, a stock market. So how to design a control problem to make the policy more robust in terms of model perturbation, and then how to combine some control techniques such that the pre-trained policy can be easily transferred to another environment. I think this transferability problem is a quite interesting thing to explore. So maybe it's a combination of model-based and model-free approach will allows to reduce the sample requirement for training a particular RL algorithm.
Great, thank you very much, Yufei. Then let's come to the next question, which is about what are research questions that received too little attention so far? And as a continuation of this question, as a field, should be focusing on a few canonical examples or developing methods and theory for a wide range of practical examples? I put it in the chat. And let's start with you, Fei, again, if that's all right.
Yeah, sure. So I think actually this question is somehow already answered in the previous discussion. So about what are the important questions in our field, and then triggered by the machine learning, and then what are the areas we can contribute to. But I think at this moment, as what Xinyu already mentioned, is about how to give explainability. Hyun also mentioned the similar question, how to give explainability about efficiency of algorithm, especially in a continuous time environment. So I think this is somehow related to how to make this particular learning algorithm robust in terms of hyperparameters, more like the time discretization, like the observation frequency and those things. In terms of whether it is important to emphasize on a canonical example, or it is for a general practical, many practical examples, I feel that we need both, right? So in a sense that it is always good to have a generic framework which can be applied to different settings, where you just adapt this framework to the setting and to different type of practical examples, which is flexible enough. But in terms of a theoretical analysis, if you have a very generic problem, it can maybe very difficult to analyze the algorithm. Then maybe in order to give a theoretical guarantees for for a generic framework, maybe it's good to assume certain structure about this model, and at least for some problems which are practically important. For example, mean variance, which is all the linear quadratic model, which we understand a lot, but which also used in practice. And by using this particular structure, at least maybe we can provide some theoretical guarantees, such that this generic framework can be, if it applied to this particular case, at least we can say something. Then I think at least then basically the practitioners can still trust this framework in certain sense. Yeah.
Thanks. No, I understand there's a bit of an overlap of the questions, but the question was really, is there something we missed so far that you think that should be considered, hasn't been kind of picked up? So, what's your take on this one? Are you muted?
Okay, I agree with Yufei's comment. I think it's good to have a generic framework, and there is another direction which is less explored, is how to use domain knowledge to simplify the framework so that the learning algorithm is easier to scale up. Because when we have a generic framework, it can be applied to many algorithms, but often they suffer from the problem of difficult to be scaled up because it depends on a lot of model parameters and dimensionality. And if we want to apply this generic framework to a particular application where we have domain knowledge in the structure, then we could probably utilize those structures to reduce the dependence on those hyperparameters and try to have a more efficient algorithm for this particular problem. I think that's also an interesting direction to explore, but I think it's less understood at the current stage.
Okay, great. Thank you very much, everyone. Then we continue with Huan.
Yes. Well, so of course, in deep learning, the training of neural network is a critical question, and well, so often the tuning and choice of hyperparameters is done ad hoc without really solid theoretical support. So there are, of course, some partial results for shallow neural networks or one hidden layer, but there is still a certain mystery why when you use a deep neural network, multi-layer neural network, it works so efficiently. So probably there should be some theoretical work in this direction. Another thing is that I already mentioned is about the validation of numerical result. Okay, so because in deep learning we sometimes obtain a very unexpected result, and it is not clear why, if it is a stroke of genius or simply a numerical bug. And so these questions are, of course, not very well studied in the academic literature and probably difficult to answer. And because, in fact, the algorithms are often trained on historical data or simulated data from a model, but in contrast to physical phenomena which occur in a relatively similar manner over time. Okay, in finance, market conditions can change rapidly, and historical data are rarely informative for the prediction of future price. So I presume that it would be quite difficult to address this problem in a general framework, and maybe it would be more reasonable at first step to focus on few canonical examples, or typically the linear quadratic or even more simple example.
Great. Thank you very much, Yuan. Then we continue with Xunyu. You're muted. Sorry, you're still muted.
Okay, can you hear me now?
Yes, great.
Okay, yeah. So I think the answers to your question are really quite individual, I would say, because different people have different tests. But in general, I think this area is still largely uncharted. Okay, to this community. I mean, to this community, it is largely uncharted. So I would rather, I mean, it's like a black box environment to us. So I would rather do exploration, try and error. Okay, instead of setting agenda, what you should do, setting agenda is like a deterministic policy. I would rather to have stochastic policy. Let us explore, let us fail, and let us succeed. I mean, you know, so just especially in the initial stage, let us just explore whatever interests us, I think. Okay? Now, for me individually, of course, I like more like a theoretical question, right? So what is a theoretical? Whether I can have a theory to explain this algorithm, well-known algorithm, for example, can I do that? Right? Whether I can explain, you know, like these temporal difference method, for example, and what is the context in the continuous time setting, right? So these are questions that interest me. Now, for me, I don't like the way of like, okay, because this is now very fashionable, so let's just, take whatever, okay, let's discretize the problem up front and then turn it into MDP, and then you take whatever available neural network and then sort of produce results. So at least me personally, I would rather sort of, explore what is the underlying, the underlying theory, what is the reason for this sort of phenomenon, and so on. So yeah. But once again, I think let people explore, because this is still in a very initial stage. Naturally, people will form a direction, I think, collectively. So that's my take on this problem.
All right. No, great. Thank you very much. No, this is a good, I think, final word for here. So thank you very much to all the speakers for the interesting talks and interesting discussion.
Thank you.
Thank you for the organization.
Thank you very much.
Yeah, many thanks.
There will be video online, and I guess the video will be shared to all the participants. So thank you very much for contributing and for attending, and bye-bye.
Okay, bye-bye.
Thanks for the effort.
Okay, bye-bye.
Bye-bye.
Bye.